Alright guys, let's resume our afternoon section. So now Renata Possobon is going to speak us about the geometry of probability space.
Thank you. Thank you for the invitation. It's a pleasure to be here, and also thank you for all the organizing committee for this amazing conference. So today I'm going to talk about the geometry of probability space, but what does that actually mean? So let's start with some metric space. We could consider some space with more structure, for example, a Riemannian manifold, but for now it's enough to have some metric space. And let P of x denote the space of probability measures on this metric space X. So I want to address the geometric relationship between this space X and the space of probability measures defined on X. So here, the geometry of X influences the space of probability measures, but this space P of X itself can carry some geometry, and that influences the space X, so tell us something about the space X. So what I want today is discuss a little bit about this relationship, and to this end I need to introduce some concepts of the optimal transport theory that will be our main tool to do that. So the optimal transport theory originated from a logistical problem proposed by a French mathematician called Münch in the 18th century. So the main idea of this problem is to transport some mass from one point to another one with a minimal cost. So for example, if you have some pile of sand in some space X and you want to transport that for some space Y that has some hole here and you need to fill it up, we can model this problem by choosing some probability in this space X that tell us how much mass I have in this pile of sand and how it is distributed on the space, and I choose another probability measure here to say how I need to put the mass in this hole, and then I choose some transport map. That is a map that associates each point X on X to a point Y on Y that tell us how to transport these masses. What we need to do is making sure that I'm transporting all this distribution to this one. So when I consider the push forward of the distribution mu by this transport map, I need to obtain the target measure here. So if I know how much is the cost to transport these masses, then I can compute how much I need to pay for that transport. So our problem here is to minimize this total cost among all these possible transport maps. In general, this map says to us for each point on X, the exact point that I need to go on Y. So sometimes this map may not exist. To avoid this problem, what we do is, instead to think about this transport map, we think about some transport plan. That's a probability measure on the product space that tell us how to transport these masses, but now we can split these masses. And the only thing that I need to satisfy here is the projection of this probability, that is our transport plan, need to match with the source distribution and the target distribution. So the new problem, the new formulation for the problem is called the Münch problem. And now we want to minimize the total cost very generic for every Hadron space X and Y, but in particular we are interested when these two distributions are given in the same space X, and we choose some specific cost function. So if X is a metric space, we can address the problem using the cost as the distance between the points, or the power of the distance of these points. And this gives to us some notion of distance of the two distributions. And this notion we call the versus-side distance. So the versus-side distance is the distance between two distributions or two probability measures defined on a space with some metric that we ask for this space to be separable and complete, just for making sure that we have some solution for this motion derivative problem. And then we define the distance between these two distributions by the solution of this problem when the cost function is the power of the distance between points. So this is not properly a metric, because if we have points very, very far away, we cannot find some finite cost. So what we do is just constrain our measures for the set of measures on which the p-moment is finite, and then we have the versus-side space being a metric on this space. So here, what we want to work is this kind of spaces, and the relationship of the metric of these spaces with the geometry of X. So here, when I say something about the metric, I'm saying specifically about the versus-side distance being a metric in the sense of the width convergence on the versus-side space. So if I have some sequence of measures on the versus-side space, and the sequence is converging for some measure mu, this is equivalent to say that I have the convergence on the versus-side space, and the sense of the width convergence is the canonical sense for that. What is very interesting is, in fact, the versus-side spaces inherit properties from the metric space. For example, we have the completeness. If X is a complete space, then also the versus-side space is complete. The same for separability, or if X is a geodesic space, then the versus-side space is also a geodesic space. More recently, some people like Otto, Villani, Lott, Stern, sorry for the pronunciation of the names, probably is wrong. They have developed a lot of calculus associated with this versus-side space, in special Otto has developed the Otto calculus. And in this kind of research, they proved that if we put some more structure on X, for example, if X is a Riemannian manifold, then the two versus-side space is a Riemannian manifold with a infinite dimension. So it's something Riemannian-like. What is very interesting for us in this context, that there exists some relationship between lower bounds for the rich curvature of X and the notion of some convexity properties and some functionals on this two versus-side space. In this context, for example, here in MEC, Christian Rodrigues and André Gomes, they proved this relationship between lower bounds of the Ricci curvature and the convexity of some kind of entropy. Actually, this is the negative of the entropy of some curve of measures, for specifically for this kind of Cauchy space of isometric actions. And in a more general context, Christian, André, and also Lisa Martin has developed a lot of things on differential and Riemannian calculus on this kind of cases. So what I want to talk with you today is something a little bit different that is associated with this relationship between X and the space of probabilities, but related with some disintegration of measures. So how we can use this tree of disintegration to say something about the space X and the relationship with this space of probability measures. So let's start by understanding what is a disintegration of a measure. In a very general way, a disintegration is something that you use to write some global measure as a combination of probabilities that are concentrated in subsets of this space. So, draw, because we like it. If you take some probability space and a partition of this space into a finite number of measurable sets with a positive measure, for every element of this partition we can write some measure that we call a conditional measure, and then we can write again the initial measure mu of this space as a combination of these conditional measures and some base measure. In a more general context, we define the disintegration for some probability space and some partition of this space in measurable subsets using this natural projection that associates each X to the element of the partition which contain this X, using this projection to address some structure of measurability and to put some measure on this partition. So we say that some subset of the partition is measurable if and only if the pre-image of this subset by this projection is a measurable subset on X. And with this we have a sigma algebra on the partition, and we set a probability measure on the partition by pushing forward the initial measure mu of our probability space by this projection. So in this setup, a disintegration of a measure mu with respect to this partition is a family of conditional probabilities such that every measure is concentrated on the element of the partition on which was indexed. We have this map being a measure map, and we also can write the measure mu as the integral of this family of conditional measures with respect to the measure on the partition. So there are many theorems that tell us when this kind of disintegration exists and when it's unique, but we are interested in this kind of theorem that instead to use some general partition, we take some Borel map and they use the pre-images of that to put some notion of fiber-wise thing on our space X to work in a more organized way. So instead of some general partition, we are doing the partition of X looking to this pre-images of this Borelian map. So when we ask some properties of X and Y, so X being separable in locally compact metric space, we can have always the disintegration of some finite and random and positive measure, mu, in terms of some measure on Y, defined by the push forward of this measure by the chosen Borel map, such these conditions. So this is also unique in the sense that if you have another disintegration where these conditional measures are concentrated on the pre-images of y, the same case that we have here, then all the measures are absolutely continuous with the reference measures on the first disintegration. So we have this measure on y absolutely continuous with respect to the measure on y that we defined first, and also all the conditional measures are absolutely continuous with respect to the correspondent measures in another disintegration. With this notion of disintegration, we define, sorry, I forgot about the examples. So some examples of disintegration is if I take, for example, the solid torus and I slice it in some vertical parts, vertical discs here. I can disintegrate some Lebesgue measure on the solid torus on measures concentrated on the discs. Or if I set some flow, for example, like this on the torus that gives us a closed curve, and then changing t here, using all the possibilities on the circle, we can cover this torus with these closed curves, and then we can disintegrate some hard measure here on measures that are concentrated on these closed curves. So now, with this notion of disintegration, we can define some disintegration maps. What is that? So if I take all the conditions to have a disintegration, I call the disintegration map just the map that associates every point y with the conditional measure when I'm thinking in these conditional measures on the versatile space. The most simple example that we have is just take the square, the unit square, and the two-dimensional Lebesgue measure on this square. So choosing as my Borel map the projection on the first component, the pre-images of every y, in this case every x. By this projection will be these fibers on the square, and then I can disintegrate the two-dimensional Lebesgue measures on one-dimensional Lebesgue measures on each point of x here. So in this case, our disintegration map is just the map that associates points in the interval 0, 1 to the one-dimensional Lebesgue measure on this guy here, x times the unit square. This is very simple, but it fits exactly into something that is the framework that we want to work on. That is called the metric foliations. What is the idea of metric foliations?
Maybe I'm understanding something wrong, but this is used, for instance, to this sort of co-area formulas, like if you have some versions, then you want to integrate
You
among
can also
fibers.
use it to that.
Okay.
You can write it, do this integration and write the co-areas in a different way.
I see. This is, I guess it's that, but it's natural to do that.
Kind of. Deixa eu preparar isso. No, it's okay. So here, thinking our metric space, I'm calling a foliation of this space just a partition of the space into closed subsets. Given a foliation of this space, I say that this is a metric foliation if the distance between any point on a fiber f has the same distance to the another fiber f prime. Then, sorry, I formulated very bad the phrase. So if I take some point x on a fiber f and measure the distance between this guy and another fiber, this has the same distance of the two fibers. So it's the same notion of a kind of parallel fibers locally.
Equidistant.
Equidistance fibers, perfect. More or less like that. So every point that I choose here, and I measure the distance between this point and another fiber, all the points have the same distance, the distance between the two fibers. All the time I can do this. So in our foliation, we can just define the quotient space. So we define this relation, the equivalence relation between x and x prime, saying that they are equivalent, that if they are in the same fiber, and then I will write as x star the quotient space, and consider the quotient map phi. And in this context here, I can define some metric on the elements, the fibers here, saying that the distance between two elements of the quotient space are the distance between the two elements of these elements by pi. So, what do we ask now? Suppose that you have your space and some metric foliation of this space, and then you take some measure in the space and disintegrate this measure with respect to this metric foliation. If, when you do the vorticide distance between two different conditional measures that are concentrated on elements of this quotient space, so each measure is concentrated on one leaf. When the vorticide space of the vorticide distance between these two measures is equal to the distance between the leaves, then we say that is a metric measure foliation. So it's a metric foliation with this condition more, when I have this disintegration of some probability on this metric foliation. And back to the example of the square, what we have is exactly that. Every time that I try to calculate the vorticide distance, I need to coupling these distributions. So the more natural coupling, the optimal one, is to take some x and x prime here and just take this horizontal line. Then the vorticide distance between these two distributions will be exactly the distance between the fibers. So this is some example of the metric measure foliation. What is interesting for us in this context is when I have a metric measure foliation, then the associated disintegration map is continuous. We have some other context on which we have this disintegration map being continuous. For example, every time when I have all the conditions to have a well-defined disintegration map, I can find some closed subset of y, and I lose a little bit of measuring here, so some subset of the y, such that the measure mu y minus mu is less than epsilon. And in this subset of y, we have the continuity of the disintegration map. Or, for example, if I take some conditions, extra conditions, on the Borel map, for example, this being bijective and the inverse of this map being continuous. Then you also have this disintegration map being continuous. Why this is interesting? Because with this we can construct types of measures and we can say something about the continuity, the absolute continuity of measures on these paths. So what we have is given all the conditions to have a disintegration map, and when this disintegration map is continuous, if the space that I choose to index my conditional measures is path connected, given 2 points on this space, I can find some path of measures given by the disintegration map. So this path is a path of conditional measures that's kind of lifted by the path on Y. If I ask some more hypotheses on X, for example, if X is a smooth, compact Riemannian manifold, and I have some conditions on my initial measure, so this is absolutely continuous with respect to the volume measure of my manifold, and I have the positive measure on all the leaves that I'm, all the fibers that I'm taking with the Borel map here. And I have some special condition on F that it's minimizing invariant. What is that? If I choose some geodesic here, then I have some geodesic in the space of the measures. If one of the endpoint measures on this space is absolutely continuous with respect to the volume measure on the manifold, then all the measures in the path, the inner measures in the path, will be also absolutely continuous. If I have not a general fiber on X, but exactly the case when I have a pre-metric measure foliation, then this absolute continuity is with respect to the volume measure on the fiber and not with respect to the volume measure on the manifold. So,
how controllable is this volume, like on the fibers? Because I mean, what kind of like comparison do you have below it? Right? Because it's a bit tricky, right, to restrict to the fiber.
yes, you can think it more or less. This is very useful when you want to work in only the whole dimension of your formation. So you forget about like the whole manifold and work exactly on this guy.
But different fibers, like there is no relation between like absolute continuity between the induced measure on different fibers.
In this case, not exactly, but you have, because you have the condition of being a metric measure foliation, it's very strict. So since you have that, of course, yeah.
Okay.
So what do we have here? So in general, the geometric arrangement of these measures on the vertex space is deeply related with what I have here in this support of these measures. So what do we want exactly is to work on this connection. So how I can construct some approach to study this relationship using these disintegration maps. So to that, always I will be in some setup that I can find that disintegration map. So it's the same kind of spaces and a Borel map between these spaces, and I take some positive and finite Hubble measure on U and disintegrating it. We define to start some notion of derivative for these disintegration maps. So it's more or less the sense of a metric derivative when we are on which we are comparing the vertical distance between the conditional measures and the distance between the fibers. Here we are using this kind of whole function here because this guy is a distance, but if I just think in distance, like in the quotient space, it's not properly a distance in all the cases. So So it's a little bit more general than that. So with this notion of derivative for the disintegration method, we define some kind of energy, taking the supremum of this derivative over all the points y on the space y. This energy is related with how this support of the measures are in our space X. More specifically, if we will ask something more for X, so now X is a geodesic, locally compact and completely separable metric space, and we do some disintegration with respect to some Bohr map, we have that this energy is 1 if and only if the pre-images of this Bohr map defines a pre-metric measure foliation on X. How to use it in something, for example, to analyze the dynamical systems. Suppose that you want to analyze the evolution of some distribution by some flow. So you have some flow on X, and here we are considering just the disk on R2 to work on this distribution. So you have some distribution of particles on the disk, and we are doing some foliation of the disk on concentric circles. So starting with this application here, that is our Bohr map, we will disintegrate the initial measure in U2. Then we will see what happened with the flow and do again a disintegration in another time t. So on. So we want to analyze this evolution here. So for example, suppose that we have two different flows. In one flow we have this spiral flow to the origin, so the particles are just spiraling. I don't know if this is a word in English, but it's kind of shrinking to the origin. And in another flow we have some kind of vertical compression. So in the first case, what will happen is my measure is just being the same, but I'm shrinking that to their origin. So, so if I think in this structure for the disintegration, I would keep the same structure for every time. So I'm just disintegrating on the circular leaves, and after some time I have the same structure to disintegrate that. So this is a kind of metric measure foliation, and when I compute the energy for this kind of disintegration, I always have energy 1. In the next situation, if I have some vertical compression, now I have no more these circular leaves, but I have some ellipses. Then the structure to disintegrate the measure is completely different. And when I compute this energy, I can have this variation of this deformation in the foliation. So for example, in this case, we can show for the one energy that is exactly the size here of the circle divided by the length of the ellipses, and then we have something that will be changing smooth on time. So I have this sensibility of the energy when I change the disintegration. So what you are working on now? So we continue to study what we can do with some dynamics and geometry in this processing space, especially associating some differential calculus for this disintegration maps. So if I change the notion of derivative, what happened with the notion of energy and what happened with this sensitivity to the deformations of my foliations, and how I can use that to characterize geodesics of the processing space, and how I can say something about the lift of the geodesics on X to geodesics on the processing space and vice versa. So today is that. Thank you so much.
Questions?
I guess I have another question. So, when you say geodesic, you only mean like minimizing distance? Or, because as I understand, there is the notion of the synthetic ridge, right? There's something like that. But there is connection also?
Yes, because we are minimizing distance on X, but we are having some minimization of distance, but with some with the same velocity of this transport on the processing space. So we are looking for this minimizing geodesics that is related to the synthetic curvature, for example.
So the point is that this synthetic curvature, it actually comes from the notion of connection. It's not only analogy. Okay.
Exactly.
And if you're working in differential in permanent manifolds, like how checkable are the hypotheses of determinants, or in this case to do actual examples? Or do they become too complicated?
A little bit complicated, because this point of when you work in this infinite dimension, it's kind of hard to test some hypotheses. And because of this, we try to take some other tools to check it. So depends what you want to do.
I have another question also, because now, if you move, for instance, to the realm of Rodrigues and geometry, right, you would be interested on maximum, like geodesics that maximize distance, actually. So, is there any sort of like hot transport notion that would try to take care of this Florentian story?
To be honest, I don't know, but I don't think so, because when you want to maximize something, you know, to non-transport is just go to infinity, because we have this notion of cost, and we just go with the case where it's impossible to do some transport. I don't know,
Okay.
to be honest.
Let's thank Renata again. And we resume at 3 with a talk by Jeremy.
It's 3 p.m. Sure. Yeah. 3 p.m. 3 p.m.
And just to remind everyone, there are some notes here on the board. Don't forget to pick up them. What I even tend to read now there. Oh, you can send to me, you can do however you want. Okay, essentially. Alright guys, so let's continue with Jeremy Guerre from the Grenoble University. Huh? Guerre. It's my time to correct. And he's going to talk to us about the rational cubic for code and the relation to heat.
Thank you very much. Very glad to be invited for the first time. So thank you for the invitation here. So I'm going to talk about cubic forwards and the theory of atoms that has been developed by Kaczmarov, Kontsevich, Montet, and Dewey. And let me first give some introduction to that theory. So the main example here will be X a cubic forward. And I should say that I should mention that like if you look at, for instance, cubic curves, they are never rational. Cubic surfaces, they are always rational. Cubic threefold, they are never rational. And this one is like the first dimension where the cubic is sometimes rational, sometimes not. So that's interesting from this for this reason. And also then a priori you cannot use any invariant that is deformation invariant because then you cannot distinguish between the rational ones and the non-rational ones. But actually, we are going to use the homomorphism theory, which is deformation invariant. But we have to couple this with another theory, Hodge theory, in a very subtle way to get theorems about birationality of cubic forwards.
Smooth ones, right?
Yes, smooth. So, yeah. So all the varieties this log are smooth, projective, and over C. Okay. So and now I start with a theorem saying that if you have X and Y, two birational smooth projective varieties over C, then there exists what is called a weak factorization. We heard about that in some talk, I think in your talk yesterday. There exists a weak factorization, meaning that you can go from X to Y, maybe not just in one blow-up, but in a sequence of blow-ups in one or the other direction. And here, these arrows means either in that direction or in that direction. And whatever direction it is a blow-up map at smooth centers. And this is very important for two reasons. First, to provide an invariant, a variational invariant that will help to decide if X and Y are variational or not. Well, you only have to do it for a blow-up at smooth center. That's the first thing. And second, you could just go from X to Y just probably in just one block blow down, but that would not be at a smooth center, and that would be very, very bad for homomorphic theory. Because homomorphic theory will be just about smooth protected varieties as well. So this theorem is very helpful. And then if we look at what happens for one blow-up, so if I have X theta is the blow-up of Z in X, where Z in X has codimension R, then there is a very well-known decomposition formula for the cohomology that I will state in this form. The PQ, the cohomology of bi-degree PQ from Hodge theory for X theta, this is isomorphic to the PQ part of X plus some part in the center, which is the subvariety Z, with a shift in the grid, like this. Where here you have K from 1 to R minus 1. So the cohomology of X theta is the cohomology of X plus R minus 1 copies of the center. And from that, you observe first that the bi-degree PQ is not preserved under this isomorphism, because there is minus K there. But you observe that the difference between P and Q is preserved. Because if you do this difference, that's always P minus Q. So if I define another degree, which is the Horsey degree of, so this is the Horsey degree. That other degree kind of preserves under this bilateral map. So what is this? This is the direct sum over P minus Q equals K of this H in Q. It's not preserved like exactly, but it's like HK of X theta is HK of X plus R minus 1 copies of HK of Z. So now we can have our very first bilateral invariant. So we can tell if N is the dimension of X, and it's also the dimension of Y. If you're wondering if X and Y are bilateral to each other, they should have the same dimension, sure. The Horsey cohomology of X, this would just be equal to the top Horsey cohomology of Y. Here it's true because if you take Hn here, then you have P minus Q equals N, but Q is non-negative and P is less than N, so that's just Hn0. And Hn0 here, Hn0 here, here to be Hn minus K, 0 minus K, with K positive, so it doesn't work. And it's the same with N minus 1 instead of N. So from that, for instance, if you take the quintic threefold of dimension 3, let's do 1. never rational. So that's dimension 1 for x. For P3 is 0. Those are different. So x is direction equivalent to P3. So that's the first observation. Is top portion W. And if you look at another example, which is our main example, so x implies a cubic fourfold, smooth cubic, then it has the following Hodge diamond. Something like this. And in this column, if you sum all the numbers, which are all 0, this is the H4, the top one. By the way, if you compare with the P4, which is this is for P4. So here it's 0, the top one, here it's 0, so you cannot decide. And that's for the best, because those Hodge numbers are deformation invariant, and we say that there are some cubic fourfold that are rational. Yeah, by the way, there are some cubic fourfold, smooth cubic fourfold that contain two skew planes, so two planes that don't intersect, and from those two planes, P2 and P2, you construct easily in a variational map, just by taking a line which passes through these two planes, and it has to meet the x at a third point. That's the variational map. So we know that it exists, and so we know, even without writing the diamonds, that this had to be 0. The H number 3, it's not this one, it's here. So it's also 0. And the first one that is non-zero is the H W2, or sheet 2. This one is 1, whereas this one is 0. Okay, but that's not a variational invariant. But, okay, from that, before I erase that, we can learn the following, that if x is birational to P4, then since it has its H2 is of dimension 1 and P4 is of dimension 0, it means that the H2 for x has to come from the block center somewhere. So then you are sure that there exists, that in every big factorization, there exists a block center Z with H2 of Z equals 0. Because if it was not here, then this decomposition will tell you that H2 will be 0 all the way from P4 to the cubic. So that is for sure. But different. Yeah, it could be 10, and then by a cordon, this 10 will drop back to 1 maybe. So we cannot say it's some number, we cannot say it's 1, okay, but we can say it's non-zero, that is for sure. And so if this is non-zero, well, the first observation is that Z cannot be a point or a curve, because there is not enough room to have a degree 2 Hirschi cohomology class in that. So it has to be a surface. By the way, it's not of higher dimension than a surface, because a block center is always at least codimension 2 in x, and here x is a 4-fold. So this has to be a surface. Okay, great. And then from the birational classification of surfaces, we know that by looking at the list, that if you have a surface and it's a minimal surface, for instance, then if it's either it's H2 Z is 0, either it's canonical under its nef. surface whose minimal model that I will call sigma, it has k sigma net. So you might think, well, it's not that great because the variational classification of surfaces, of course, those are like the one that we don't know very much about. They are called like the general type, or like K3. I mean, K3 is not general type, but I mean, it contains all the general type. So that's not super good, but from the point of view of Gromov-Witten theory, you should be very happy because we'll see later. But every variety with KNF has a very special property from the point of view of Gromov-Witten theory. In the theory of atoms, every smooth variety with KNF has only one atom. One. It's like an irreducible, just one. Yes, so that's the first thing that we learned about this stuff, just with this very coarse invariant, which is just the Hoche degree coming from Hoche theory. And now there is a conjecture by Hassett, which says that x, same x, and the cubic fourfold is rational if and only if the primitive cohomology of x is isomorphic, as we said, Hoche structure, to the middle cohomology of projective K3. So, yeah. So what is the primitive cohomology? The primitive cohomology, it's the so first, what is the ambient cohomology? We have heard about that in Giovanni's talk. The ambient cohomology is you take all the cohomology of P5, you pull back to X, and this gives you some classes in the end. Which classes? It gives you the one, this one, not the two, this one, and this one. And then you have the other classes. But if you, just the two, it's a 20. So the primitive cohomology of X, it's Hoche diamond, it's just in H4, because you remove these classes here, the one from P4, from P5. And this is just 0, 1, 20, 1, 0. So these numbers are just the same as for the middle cohomology of the K3. So, yeah, that's the first observation. And this is the conjecture. It's an if and only if we look at integral Hoche structures. So now, the theorem is that, the theorem is just this direction, but unfortunately, only with a few Hoche structures. So this means that I prove that if X is a rational smooth cubic fourfold, then it's cohomology H4, primitive cohomology in H4 with Q coefficients instead of Z is isomorphic as Q Hoche structures to the middle cohomology of a projective K3 with Q coefficients. Okay, so it gives some evidence to that conjecture. And as a corollary, well, this gives, for instance, what they prove these authors like Kontsevich, Katsakov, Kontev, and Münch. They prove that the very general cubic fourfold is non-rational. And so, very general X is irrational. Why is that? For a very general cubic fourfold, the only algebraic classes that appear in the middle cohomology are exactly the power of the hyperplane class, the one that is not in the primitive cohomology. So this means that 20 in this Hodge structure, even as a Q Hodge structure, it contains no algebraic classes at all. No algebraic classes. But if you show that direction with Q, then here it's a projective K3. So here it has like a hyperplane class. Okay, so that's a contradiction. And yeah, so as a remark, and it goes along the line of what I explained earlier, this theorem is actually proved, is proved by showing the following result, that if X is rational, then in every weak factorization, there exists a blow-up center Z that is a K3. So, with a very coarse invariant of Cauchy degree, we were able to say in the first place that if X is rational, then there exists a blow-up center with K and F. And here, it's a better result in the sense that, thanks to the theory of atoms, we go from K and F to K, and from K and F to Z being just a K3 surface. Yes?
For your theorem, is the converse, are there any counterexamples for the converse for your theorem?
Like this?
Yeah.
Not known. Yeah, so you're asking. So I should say, Asset has a complete classification of cubics that behave like this. Okay, so we know exactly which cubic should be rational, and also a classification of cubic like this. So the one that are here but not here, we can like have specific examples, or at least we know things about them, but we don't know if they should be irrational, but we don't know that. Yeah, so how do we prove this remark? How do we prove this crucial remark that implies this theorem? We have to go from K and F to Z being a K3 surface. And for that, I have to use just a little more than the Cauchy degree, right? So this is what is called the atom theory. So this is so refined invariant, refined compared to the Cauchy degree 2, compared and the result is that K sigma net will be replaced, thanks to this, it will be replaced by that K3. And what is the rough idea beyond this new invariant? So this one, we got it from the decomposition formula in cohomology for the blow-up, the one that was written here. And this was an isomorphism as Z crush structures, and in particular as Q vector spaces, if you like. This was not an isomorphism of rings, definitely not. But somehow, this decomposition formula is an isomorphism of quantum rings. So this has to be more precise, but the blow-up formula, this with the blow-up formula is an isomorphism of quantum rings. Okay, let's take a look at time. Very good. Prediction. So, yeah, so fortunately we have seen the quantum product this morning, thanks to Giovanni. Maybe, should I repeat it? Yeah, I think so. So if you take the basis of your cohomology, X dimensional coefficients, and even like a gradient basis, more appropriate. And if you take Pi lower I or lower j, such that Pi j product is either 0 or 1, depending on whether I and j are equal or not. So that's the dual basis with respect to this perfect pairing. Then you can define, so we can define for any tau, which is an element, there are several things that you can do. You can take tau in here, but let me do the general version. So you take a vector space in here, gradient vector space, and you choose a basis, alpha k basis, gradient basis of this vector space. So for instance, V would be the even part of the cohomology, or it would be the degree 0 Cauchy part of the cohomology, or it would be even the Hodge part of the cohomology, just Hodge classes. In the original paper, KKPY, they choose this. Okay. So that's it. And then you put a formal variable. One formal variable for each element of your basis. And then you define this formal element tau just by tau of the sum, like this. Okay, so it is just a formal element of V. And then phi I multiplied with phi j, where the multiplication is defined along tau. This is just a sum over like j and beta of phi I, phi j, phi k, tau, n times. Erase this. Here, this bracket means Gromov-Witten invariant of x, genus 0, 1, 2, 3 plus n markings, and curve class beta. I'm not writing everything, but we have seen that this morning. So that's the Gromov-Witten invariant, just in genus 0. And then you put the dual class of phi k. You sum over all possibilities for k. Then you divide by this number. And then we have this special variable q that I haven't introduced, which just keeps track of the degree. That's called the logical variable. Let's just pretend that it's just a formal variable. It's more tricky than that, but I don't want to go in this detail. And I think it's all. Then you have the Euler vector field. So that's an element of the cohomology, but with the formal coordinates. And you define just as this. That was also in German stock. So, and then there is the main character of the atom story, and one of the main characters, which is denoted by kappa tau, and which is the Euler the multiplication, quantum multiplication by the Euler vector field. So just this. So what is this thing? This thing is an endomorphism of some kind of vector space, which is the cohomology of X. But because of all these formal variables Tk, because of this extra formal variable q, this has to be base changed to a divided by r, and this r is, to be precise, it's just like formal power series in q and the tks. Okay, so up to annoyances coming from this formal power series. This is basically just an endomorphism of your cohomology. So, and furthermore, if you choose like a basis, as we did, then in this basis, this is just a matrix. So this thing is a matrix with coefficients in that ring. That's all what it is. So now comes the very important theorem due to Iritani. This theorem is exactly the same as the blow-up formula that I've written on the blackboard before. It's the same spirit, but with this quantum multiplication instead. So it says something stronger than what I'm going to write, but in particular, so it says some isomorphism between the quantum D modules or whatever, but in the end, this implies that if you have x theta, the blow-up x at some smooth center z, then the endomorphism kappa tau, but for x theta, this is conjugated as an endomorphism, conjugated to the one for x and copies of the one for r, for z. So that's it. And here, so we have to be a little careful. First, this conjugation. So you can, if you prefer, you can see that as a conjugation of matrices. Matrices should be in the ring R, but actually you have to be a bit more careful about that. This is as endomorphism in some R hat. So that's one thing. And secondly, and I will get back to this very quickly, and secondly, you may see that here it's a tau tilde, and here it's like tau 0, tau k, they are different, different notation. So in Iritani's theorem, there is explicitly, he says how to go from this notation to this notation, and that's by a change of variable. So this is a change of variables. And also, I should mention that here, this theorem, this is space.
What is hat?
Sorry?
Hat C. It's not really correct.
R hat.
Yeah.
Why did I put a C here?
What is this?
Yes, I haven't explained it. Yeah. So R was written there. So that's R. I did not by RC, you will see here instead. Okay. And R hat, it's, you have an extra formal variable noted by Q that you have to the power plus or minus 1. So it is like a logical variable, but with the difference that it could have negative powers as well. And that's a very, very tricky problem. Yeah. So from that you see, for instance, that this contains the usual R, because just don't have this. You have also, so I'm cheating a little bit because, so here here this is logical variable with respect to x, and the tk with respect to x. Okay, so here is r, the previous r with respect to x. But you can also ask the question about r x tilde. So different logical variable, and this one is this. Okay, let me not put this subscript. This, and the tk are different as well. Okay, so it just happens that this embeds as well into this one. And what is this map? I don't really want to write it, but I can only say that if you take q tilde, the logical variable here, to the power le, where le is a line in the exceptional divisor. So vertical line in the exceptional divisor. Then you have the logical variable attached to that line. Okay, and that line under this map goes to q, or more or less like goes to q times, let's say, 2 minus 1. And so this gives like a meaning of this extra formal variable q. Yeah, that's the technical part. It's just that it's required because here, if you put r, then it doesn't make any sense. Are you talking about r, the ring with respect to x, to z, or to x tilde? So you need a common ring. And you may wonder about z, by the way. So the r with respect to z, it doesn't embed a ring. It still has a ring map to this r hat. So this r hat is just here to make sense, even make sense of a theorem like this. Those are like matrices with coefficients in different rings. So if you want to compare them, then you have to enlarge your ring so that you can compare them. So that's all. That's all, except that to do that, basically you don't need the minus 1. But to get the theorem of Florentin, you really need to invert this q here. So somehow to invert the line, the vertical line. And that's well, basically that's just due somehow to the fact that Florentin's formula comes from a localization formula somehow, and in localization formula you always have to invert a lot of terms. So that's not surprising from this perspective, but it will be very it gives extra difficulties to the field. So
do you think that proving some sort of thing only for small quantum homology restricted to vertical curves only, it should be easier, or?
So I don't think that's possible for the small quantum homology. Right? You don't expect this to be an isomorphism. So yeah, so that's one thing that we should say about this change of variable, is that you should never trust it. Right? You should never trust this change of variable. If you observe, so these are formal variables in V. V is a subspace of that. Okay? So you can take, for instance, Hodge classes in that. Then you may wonder, if I have a Hodge class here, is it true that the change of variable sends it to a Hodge class here? Well, don't trust it, prove it. That's all what I'm saying. Because it's not, nothing implies that directly in the notes. It is true that Hodge goes to Hodge. It is true that Horseshift 0 goes to Horseshift 0, or even goes to even. But other things are not true. It is true that if you have, it is certainly true that if you have a G action on your varieties and your block center are G-bind, G action here is compatible. This is compatible with the G action. But all those things you have to prove. But for instance, you're asking about small quantum, which is tau equals 0. That's what it means to be the small quantum product. So is it true that 0 goes to 0? No. yeah, I don't think that is true. Yeah, so so that's the main theorem, which, if we forget about a lot of difficulties, technicalities, like this hat here, or other things, then you think, okay, so I have some invariant now, something that is invariant that behaves well under blow-up, which are, since these matrices are conjugated, you can take like eigenvalues and generalized eigenspaces and compare them. And an atom, basically, is just a generalized eigenvalue, generalized eigenspace of this. This would be an atom of x theta, and the same on this side. And they behave under directional transformation like additionally. So that's the rough idea. But then you have then first, so far you don't have anything that is, I mean, here everything is deformation invariant, because it's just using Gromov-Witten theory. So if you want to have something that is not deformation invariant, then you have to have some compatibilities with some structure that is not deformation invariant, and that's the Hodge structure. But Hodge structure is over Q, and not over Z, better even, but not over C. So there are a few difficulties that I will not spend too much time on it, but just to mention that first you have to be very careful and to replace this C everywhere in the Eritan's closed formula. To replace it by better would be a Z, but that's completely false, because those matrices, they are defined by Gromov-Witten invariants, which are just rational numbers due to orbitonness of the polarized spaces. So Z is out of reach, but we could ask for Q, and unfortunately it's not true either. So the best you have is to replace this by K, a number field. And you can control this degree. Like for 4 folds, you just have to add, from Q, you just have to add, maybe just add, and yeah, don't remember actually. Well, you had a few things, and yeah, you just add, it's just, you can take K equals Q bracket I. So, that's the first thing. The second thing is to see if, so refinements of this theorem. So first, as I said, complex numbers replaced by number field. Secondly, this V here, this V here replaced by the Hodge classes in X, or the Hodge shielded with 0 in X, would be 2 good candidates. So that you have to prove that the change of variable sends one to the other. That's non-trivial. Non-trivial, but kind of already done in Eritan's book. You just have to follow it carefully. And then, once you are in this situation where you have a number of fields, so not so far from Q, and Hodge classes, you may wonder whether this is like a conjugation of Q Hodge structures. And that's almost true. So, yeah, I will not talk more about this, but this is almost true that we can promote this to a conjugation of Q Hodge structures. To be very precise, it should be just K Hodge structures. That's not enough for what we want to do. So you have to change it with you know, an extra property of Gromov-Witten theory, which tells you that even if this parameter, this deformation parameter has coefficient in K, then it's not too far of being a morphism of a Q Hodge structure. It's a linear combination of morphism of Q hash structures with coefficients. It's like this. Kappa tau is the sum of Si kappa I, where these are morphisms of Q hash structure, and this they form a basis for the number of P under Q. So that's the thing that set the day for the Hodge structures. Yes.
Even for the classical homology, do we
Sorry.
know, for the blow-up case, do we know if the Z Hodge structure are identical in the classical case?
In the first theorem that I wrote,
Yeah.
yes, yeah, that's an isomorphism of Z Hodge structures. Yeah, but it's not the same there, right? So this isomorphism you cannot use it in the atom theory.
Or for the decomposition of
Yeah.
homology of blow-up and Z and pieces,
Yeah,
is this an isomorphism of D structure or?
of Z Hodge structures.
I
Yes.
see.
Yeah. But here it's a whole mess. Like even like the cohomological degree, it's just not preserved. It is preserved if you like this. So the conjugation is given by an automorphism of your space of the vector space. This automorphism is homogeneous of some degree, of degree 0 actually. But homogeneous in a sense that is not the usual cohomological degree. You have to assign a degree to all the variables tk that are present in this tau, and also to the logical variable q, and then that mixes everything. Yeah. So you cannot say with the quantum product, you cannot say that if you have homogeneous classes alpha 1 and alpha 2, that the degree of alpha 1 times alpha 2 is the sum of the degrees. That's not true anymore. Not for the usual cohomological degree. Yeah. Let's see what time it is. Yeah. So the biggest problem is actually was not with this with the fact that it was over C. The biggest problem was with this hat and the fact that we invert. We really have to invert here some the vertical lines in the floor. So the big issue is that half hat it depends and it inverts. Here we invert the class of the vertical line, and then this means that it depends not only on x or on x theta, but on the map x theta to x. So it really depends on the blow-up map, meaning that if you do this, and that's what you will do in a weak factorization, you want to go not only from here to here, but then from here to here. Then in there, you will have a first, you will apply one time Italy's blow-up formula and another time. Okay? And the two times will be different. Like you will have R hat 1 and R hat 2, and they will not be the same. Okay? So if you know something about this variety and the centers, then you know something about this variety in R hat 1, but you don't know what happens in this other, just different matrix, different story, end of the day. You don't know what you do with that. So you have to either you enlarge your ring into something that will contain this and this, but I tried this and it's very, I couldn't succeed in that way. So either you go to a smaller ring that is still enough, say something relevant about variational geometry, but like a uniform ring for all varieties. So the solution will be to look for a map. Actually, a map for every R, for every some ring such that you can extend it. You can extend it to our hat. Where this is a common nut depending on x theta, or even worse, x theta 2x, like the Mach itself. So I bet there is not so many choices for such a ring. There is an obvious one which is a 0, that always works, but it gives nothing. So that's maybe not a good thing. It's not very well motivated at this point, but this S has to be first a ring of formal power series, and secondly, for some extra technicalities that I haven't discussed here, you need also this formal power series to have like roots and things like that. So in the end, you take the Levi-Cevita field in one variable. So well, that's not too bad actually to work with this one. And then you also have an extra variable b, and this is just a polynomial in b and b inverse. This will be to keep track of the degree. I haven't talked about the degree at all, so let's forget about this part. And what is this? Well, this, an element here, is just a sum of x and a to the n. That would be just the usual formal power series, except that here n is a rational number. And so that's for this q, and this q is the fact that these coefficients are in q.
Explain to me the coefficients Florentin.
I'm not done yet. So such that for every n in q, if you look at how many xn are non-zero, knowing that knowing the number of n such that xn is non-zero and n is less than m, this is finite. Yeah, you need this, obviously. It's a condition just like the Lorentz series, basically.
You don't want to take Q bar instead of Q?
No, Q. I do want to take Q. That I will extend further to K, a number field, and I prefer to avoid Q bar, even though I'm not. Maybe that will work as well. And in that field, so that's a field, and in that field you have an extra ingredient, which is, as for any formal power series, you can define an absolute value, which would be a non-Archimedean absolute value. So if you take P, the minimum value of all n such that xn is non-zero, then this absolute value here will be just defined to the minus p. So this is an absolute value, and it is non-Archimedean. Okay. Why do we care about this absolute value? It's just very convenient because here we look for ring maps from this to here that will extend to this guy. And this guy, remember, would have inverted something in here. And that affects a lot the number of ring maps that you have. And how do you define a ring map? You may want just to define it for this, for instance, is just Q tk to somewhere and then extend by linearity in a continuous way. And that doesn't always work. Then you have convergence issues. For instance, imagine if you have q is degree 2 and tk is degree minus q, and then the term q times tk you send into a degree is degree 0. So if you want, for instance, homogeneous mass, then you will send it to a degree 0 element here. So that's a number basically, and an element of that field. And on the other hand, the infinite sum of q times tk to some power n, this infinite sum, will be just sent to this infinite sum here. So by this I mean something like this. And you know that for this series to converge, like if this is a complex number, then you need like the absolute value to be less than 1. And here it's the same. You also need some to be careful about convergences. So this absolute value is just very useful. We don't really need it, but it's really useful to be able to say when these maps are, when we define them on generators, when do they extend or not. Okay, I have to finish soon. So yeah, so you have to be careful about convergence issues, as I say, but I think that I will not say more about that. So now, remember we have this endomorphism of this matrix, and you know how it goes along lower absolute centers. And you know that by computation, all the generalized eigenspaces are preserved. But then you want to go like from here to here. So instead of working in any of these rings, you push everything to a common ring S. So do we know that some ring map are at S? And you will look at this endomorphism instead, right? The matrix with coefficients in S instead of this one, and compare those for different for x1, for x theta, and for x2. And so from that, we will first compute the generalized eigenspaces, which are just the kernel of this endomorphism standard Dn, but then some power. And those are the blocks that behave well under the Eric formula. So these are the kind of variational invariants, and this we can call them coarse atoms. I think that was what you said. And from that, you want to extract some invariance or some property that is preserved under ring factorization. And so I would say if you have property star, some property on this, if you have some property on this that is valid for almost every evaluation map and for all eigenvalues lambda, if this property is true, then we say just that x. So this is a reference to tau, which has a reference to the variety of study. So we say that x satisfies this property star. So basically you have to hook up a property of vector spaces that property of vector spaces that, for instance, is true. The property will be it's not just vector spaces. You are also able to use more structure like rigidity. So this property, basically you can take any property that is stable under direct sum. So meaning that if you have two vector spaces A and B and they all both satisfy star, then the direct sum will also satisfy it. So that's one thing that is necessary. And then you have the main proposition following from Newton's growth formula that if Z has property star, then property star is preserved under the. So it's true for X even and if it's true for X theta. And if Z has not property star, then X theta cannot have it either. So now we can finish soon. As a consequence of that, if X is birational to Y, if X fails the property, and if Y satisfies the property, then it means that somewhere in the weak factorization there is a blob center that fails the property. Because if every blob center satisfies the property, then you can pass the property from X to a blob. So there exists a blob center Z that fails the property. So what kind of property am I talking about? And we'll just introduce a few numbers. Then I will say one comment and then I stop. So the first number will be the dimension. So it's a number attached to to the evaluation map and the eigenvalue. And it's the dimension of the generalized eigenspace intersected with the Hodge-Lopez. So it's counting how many different independent algebraic classes you have in your generalized eigenspace. That's the first one. The second one is the same. That it's also a dimension, but with the Horseshoe degree K part of your. So here it counts the Hodge classes, here it counts the degree K, Horseshoe degree K classes. And here it's a bit different. It's you take your endomorphism and and you restrict it to your generalized eigenspace. If it was an eigenspace, then this matrix restricted to that would be just 0. So the rank will be 0. But here it's a generalized eigenspace, that makes a difference. So the rank can be something more. That's like the size of the Jordan block. And so then you have two properties, two different candidates. You have the property given in the KKTY paper, and you have the property given in my paper. The first one is to say that either you have no degree 2 Horseshoe classes in your generalized eigenspace, or you have at least one degree 2 Horseshoe class, but then you must have at least 3 algebraic classes that are independent. And the other criterion is either you have no Horseshoe degree 2, or you have at least one Horseshoe degree 1, or this rank, gamma, has to be more than 2. And then how do we conclude from that? For instance, in KKPY, what you see is that first complicated computation is to show that for P4, show that for a cubic fourfold, this is always satisfied, always, and this is satisfied only for the very general one. So that's computation that you do, but you have the spaces, the cubic or P4. But then you have to know about the centers. Right? So we are in the situation where P4 satisfies X phase. If you take X very general for KKPY or any X for my paper, then you know that there is a lower center Z that fails this property. So the question now is to understand what are the points, curves, and surfaces that fails this or that. And we already know that if this is non-zero, the canonical of the surface, so first it's a surface and then its canonical is an F. That's the first thing I said in this law. So now, we come back to Gromov-Witten theory in the case of surfaces with K and F. They are very special because then you see that this matrix is a nilpotent matrix. Nilpotent. So it has just one generalized eigenspace. So it's just a whole cohomology. And since it's a whole cohomology of a surface, it has at least 3 algebraic classes, like 1, hyperplane, and point. But, so, there is no block center failing the property of KKPY. So that's the proof that a very general X cannot be irrational to P4. And in my proof, what we have to do is to show that this property is just enough to decide that if a surface fails that, then the surface must be a K3. K3 surfaces are very, very special from the point of view of Gromov-Witten theory. Basically, all the Gromov-Witten theory is 0, except the very trivial part, which is coming from the usual cup product. And that part of the cup product is rank 1 and not 2. That's a very easy computation. You have nothing to do except use the dimension axiom. So yeah, that's all I wanted to say. Thank you.
Questions?
I have one. Yeah. So at the beginning, when you established that blow-up formula, you mentioned that the deformation thing, right? So it's deformation invariant. And you mentioned somehow how to get this stronger, right? Like leave the deformation class. So how should I put the Hodge structure inside it somehow? Like it's only restricting the V, or it's something else?
Yeah, so that's a good question. So first you have to restrict the V. So it's all about this endomorphism. Does it preserve the Hodge structure or not? If tau has coefficients in Q, this is a morphism of Hodge structure. That is just because Gromov-Witten invariants are defined by an algebraic cycle. Yeah, and this has to be not in Q, but in Q bar in the paper of KKPY or in a number field, more precisely. And this is just enough to be able to conserve this morphism of Q structures. Yeah.
But there will be still deformation invariants, right? Because of the Gromov-Witten?
No, that's not true. It's like you have a direct sum of all these generalized vector spaces, and your Hodge structure will be aligned with this decomposition. Okay, but it doesn't vary. I mean, it's not deformation invariant because for the very general one, fans of the cubic, the very general one, this intersection will be just 0, whereas it can gain some algebraic classes. Yeah, so it's not. This is the subtle part. That, but if you look at this criterion, that's very funny because here there is nothing with reference to Hodge theory. I mean, except the Hodge theory. And that means that this property is deformation invariant, actually. So that's This one is just for the very general cubic fourfold. This one fails for every cubic fourfold. And that, the combination of the two can be used, for instance, to show that certain varieties, certain class of varieties, satisfy, for instance, this criterion. That's very non-trivial, because to satisfy this, you have to know that for every evaluation map, so basically for every parameter tau, you have this property. And as Giovanni said this morning, you don't know this matrix for every tau, because for that you should know the big quantum cohomology that is out of reach. So you just know tau equals 0 actually. That's the thing you know. The rest, you don't know. So, but by combining these two criteria, then you can learn, for instance, if we have one example, I don't know if you're talking about it or not, but okay, in Rio, if you're going to Rio, then you will have this example where we can prove that. So the example is the Vera fourfold. It satisfies this, and it satisfies this. But that's like something non-trivial to prove, because we show that without knowing what's the matrix.
And what do you consider about the Vera for the second condition?
The Vera for the second, it always fails. Yeah, yeah. Yeah. So, yeah. And by the way, I think the more I think about this atom theory, I mean, okay, right, that's good, but I think in the end, all the invariants we have, I mean, if we forget about that now and just keep that, which is a bit better now, and if we think about other invariants like the spectral dimension that was mentioned by Ludwig, all those are deformation invariants. So, yeah, so in the end, I think we still don't, we have not like one invariant of atom that is not deformation invariant, except this one, but it's not really needed anymore.
So may I ask you about this last step? So so there are these surfaces of general pattern, you have a K3 type of structure. So how do you actually exclude them? So I understand that.
Yeah. So it's when you compute, so you compute kappa tau minus the zero part of kappa, the degree zero part in tau. So and you write this matrix for a surface, for any surface with KNF, for any surface with KNF, then you have the basis where you have the H is like this, and the same here. Then this matrix is very special. It's of this form. There is something here that's not think too much about that. So this is the matrix. It's an important matrix, as you can see. So that's why there is only one atom, one generalized eigenspace, the generalized kernel. And what are those matrices? This one is a matrix that we don't even know. We never know how to compute this part of the cohomology. But this is excluded by the fact that, I mean, I want to see which surfaces are failing that. So, meaning this non-zero, and this 0, and this strictly less than 2. That's what I want for my surface. So I have H1 equals 0. So I don't have this part. So I don't have it to explain to you. So what is A and B? So B, first, it's just, so in your surface sigma, it's just a cut product with C1 of sigma. So it's the perfect pairing. Perfect pairing at this class. So if this class is 0, then it's not perfect at all, it's just 0. And if this class is non-zero, then it has rank 1. It is not completely 0. So C1 non-zero, value of B is 1, and otherwise it's 0. And A is just a 0 column, except for the last one, it's either 0 or 1, depending if this is non-zero or not. So again, this is rank 1 if and only if C1 is not non-zero. So from that, you see that this matrix is rank 2, 1 here, 1 here. If and only if C1 is non-zero. And if C1 is 0, then this is the 0 matrix, this as well, only this is the non-zero entry. So it has rank 2, exactly, no, well, maybe there is U as well, but at least 2 if C1 is non-zero. So then you learn that you have a variety surface with KNF and C1 equals 0. That doesn't mean that it's a K3. But if you ask that H1 is 0, then it's not an abelian surface. That's why I put this extra condition. And then if you have H1 0, C1 0, and KNF, you're almost a K3. If furthermore you know that your H2 0 equals 1, which you do by other means, because this atom of the surface has to embed in the atom of the cubic, which has this H2 0 equals 1. So it cannot embed as being like a dimension 2 or 3, it's dimension 1 part. So you know that H2 0 equals 1, and then it's definitely a K3. I mean, the minimal model.
Okay, let's thank Jeremy again. And we resume at 4:30. We now have Andrei Sodanchenko. Did I say that right? Great. Here from the company, and he's going to tell us about the variational geometry of the hypercandidate manifolds and the real projector.
Thank you very much. I would like to thank that when I was invited to this conference. So I will talk about my joint work with Yekaterina and Commissioner Rodrigues. The work is about variational geometry of hypercandidate manifolds. And so first I would like to explain what the hypercandidate manifold is. For this talk today, the manifold will be always the following thing. So we have compact manifold for the Riemannian metric G inside that. So I will first assume always that it is simply connected, and also that the polynomial group of this metric is equal to SPN. So one of these groups that enters into the classification for the usable polynomial group. So this is the compact form of the symplectic group. So from this, everybody knows very well that by polynomial principle you make deduce that there are some tensor fields on such manifolds. So in particular, there are some complex structures. The manifold by polynomial principle, because this group commutes with the action of quaternions. So this manifold admits also an action of the quaternions on the tangent bundle that is integral. In other words, there are three complex structures that satisfy the usual quaternionic relations, and they are parallel with respect to the connection, so that if we consider the corresponding data forms, the corresponding group forms, then they are closed. And so this metric is scalar with respect to all of these complex structures. Okay, so what will be more important for me is that such manifold is actually symplectic in the complex sense. So the complex manifold that means symplectic form. It is a complex manifold in many different ways. So if we fix one of these complex structures, I, for example, so So let's fix I, and then consider the following linear combination of the Keller forms. So omega J and omega K for the other two complex structures. So then this turns out to be a holomorphic symplectic form. It is a holomorphic form, so it is a form of type 2-0, closed, and non-degenerate. Well, non-degenerate means that if we take the self-product, the top power of this form, it will give us a section of the canonical bundle. So this sigma I, so here it is written that it is a 2-0 form, and then the power n of this sigma I trivializes the canonical bundle. So our Heidegger manifold is a Calabi-Yau manifold. Its canonical bundle is trivial, and also because of this condition that this simply connected, actually we want to show that this symplectic form is unique up to rescaling. So this space here is one dimension of the space of global sections. So MI, such manifolds sometimes are called irreducible or morphically symplectic manifolds. Yeah. So they may be projective or may be non-projective. And so my main object of study today will be the birational geometry of this kind of complex manifolds. Okay, so before going to birational geometry, let me just recall some examples. If someone has forgotten, so there are some examples of Heidegger manifolds. The K3 surface, for example, that was prominent in the previous talk. So any complex K3 surface is a Heidegger manifold. For example, this one, a quark in K3 is a K3 surface, and what is explicit in this example is the manifold, the smooth Metzi infinity manifold, and the complex structure which is induced from the complex structure of the projective space. The metric here is not explicit, so the metric exists by Calabi-Yau theorem, and together with this metric there exist the other complex structures that form this triple IJK. And in general, somehow this will always be the case, that the metric in all these examples is not constructed explicitly. It is deduced from this difficult analytic theorem of Calabi-Yau. So for K3 surfaces we have this Heidegger structure. Then the next example, well, of course there is an easier example, which is just the torus, compact torus of dimension 4, which is the quotient of the space of quaternions by length. But I don't include it because of this condition that I want to work only with the simply connected manifolds today. So then the next example actually is the Hilbert scheme of points on a K3 surface. So what is it? If we start with a complex K3 surface, we may take its symmetric powers. That is pentuples of points on such surface. So the space of such pentuples, the symmetric power, is not a smooth manifold also today. So my manifolds will be mainly smooth. So I want to study the birational geometry of these smooth manifolds. And the singular manifolds arise only as some auxiliary pool. So in this case, to get a smooth manifold, one needs to resolve the singularities of this guy. And the resolution, there is a minimal resolution of singularities. It is called the Hilbert scheme of length n subschemes of S. Okay, so you can also describe it as the Hilbert scheme. So the difference here between this space of pentuples and the Hilbert scheme is that for the Hilbert scheme you need to remember the non-reduced structure. So when the points on the K3 surface collapse, they come together, then somehow there are different ways in which they can collapse. So what they form is a non-reduced subscheme of length 2 in a K3 surface. And this non-reduced structure is what we have to remember to construct this smooth smooth manifold, the Hilbert scheme of n subschemes. Again, there exists element on this manifold, and it is also simply connected. So that is the second basic example. And then, analogously to this example, one may construct the following thing. Instead of a K3 surface, one may start now from these complex tors, right? So these tors, which I have mentioned already, it is actually hyperthermic, but it is not simply connected. Well, then one can do the same thing. One can look at the Hilbert scheme of points on such tors. And it is also not simply connected. But then this Hilbert scheme of n+1 points on the tors, it has a map to the tors itself. So I can take these points and consider their sum using the group structure on the tors. So this is actually the Albanese morphism from this variety to, and this is the Albanese variety of this Hilbert scheme. And then, so somehow the non-triviality of the fundamental group is killed in the fiber. So the non-triviality of the fundamental group comes from this Albanese variety. And if we look at the fiber of this map, this will be also a simply connected manifold, a smooth, simply connected manifold that admits hypertelemetric. It is called a generalized Kuma variety. So these are the two main series of examples of hyperthermic manifold, the Hilbert scheme of points on a K3 surface and the generalized Kuma variety. So they exist in every even dimension. So the K3 surface of dimension 2, this Sn guy is of dimension 2n. And Kn is also of dimension 2n. But there are more examples constructed by operating, the exceptional examples in dimensions 6 and 10. Which I will not describe. So I will mainly be interested in this Hilbert scheme today as an example of what I will be talking about. I'll use some particular example of a Hilbert scheme of points in K3 surface. And then these are all examples we know of these varieties of this type. Today, there are no more known examples. So my talk today is a variational geometry of hyperthermic manifold. So I have mentioned already that they have a trivial canonical bundle. And then birational transformations between such manifolds with trivial canonical bundle, they are kind of special because the canonical bundle on the birational of the manifolds is trivial. The birational maps cannot blow up or blow down devices actually. So these birational transformations are something similar to flows. So this type of birational transformations in general is, the first example of such a birational transformation is called Münch flow. So before going to the discussion of this conjecture and our results, I wanted just to say a few words about this basic example of a birational transformation that actually is a model of a more general birational transformation that I will study. So let me tell a few words about what is a Münch flow. It's a local model, so it will be a local model for the general birational transformations between symplectic manifolds that I will study afterwards. And then, the idea of the Münch flow is that somehow we know that one basic example of a symplectic manifold is the total space of a cotangent bundle of any manifold actually. In the case of the Münch flow, we will look at the cotangent bundle of Cpn. And the idea of this birational transformation is that we can contract the zero section of this total space of the cotangent bundle and then blow it up in a different direction somehow, in some sense. So let's have a look at this construction more closely. So my variety here, so I'll call it X. So this model will be called X. So this is the total space of the cotangent bundle of CP K. So I want to take the projective space of dimension K. So V is the complex vector space of dimension K plus 1. And so how to construct the zero section of this total space of the cotangent bundle? So one way to see it, I think, is to use the following. So let's recall that we have the Euler sequence on the projective space. So this cotangent bundle is actually embedded into the bundle of the following form. We start and tensor O of minus 1, where this O of minus 1 is a tautological subbundle in V. So if we compose this embedding, this first arrow, with the embedding of the tautological bundle to V tensor O, then we get an embedding of this cotangent bundle into the trivial bundle with fiber and the morphisms of the vector space V. So the total space of this bundle, omega, the total space of the cotangent bundle will be submanifold inside the total space of this trivial bundle, and the total space of the trivial bundle is just the product of the projective space and this affine space of the endomorphisms. So more precisely, so how to embed this more concretely, we can somehow describe this total space as a subvariety inside of this product of the projective space and the affine space. Well, if we recall that the fiber of the cotangent bundle over the point U, so U here is the point in the projective space, so the cotangent space is formed from the quotient of B by E. This is subspace generated by U to this one-dimensional subspace. So we may identify the elements of the cotangent space with such homomorphisms. And every such homomorphism is an endomorphism of V. First, map V into the quotient canonically. Then we apply these elements if we have some homomorphism from V mod Cu into Cu. And then we compose with the embedding into V. So by doing this, we get an endomorphism of V. Yeah, and so then such endomorphism of V is an endomorphism of rank 1, such that the image of this endomorphism is contained in this line spanned by U. And also the line itself is in the kernel of this endomorphism because I'm taking the quotient here. So actually I can describe this total space of the cotangent bundle of the projective space explicitly as follows. It is a set of pairs, a point in the projective space and an endomorphism, such that the endomorphism has rank at most 1, and the image is contained in this line, and it is nilpotent, square is 0. So now how to construct the zero section of this one? What is the zero section? The zero section is the set of points of the form U, comma, Z0, when the endomorphism is 0. So to construct the zero section, one may just project to this affine part of the endomorphisms. So this projection will just construct the zero section of this cotangent bundle, and the result of the projection, so the image of X inside of this space, is just the following thing. It is a set of matrices, basically matrices of rank at most 1, and the matrix is important of induced. So this is a singular variety inside of the affine space. It has one singular point at the origin. Okay, so this is the first step of doing the flow. So this contraction is the method constructs the zero section. So how to do the second step? For the second step, we'll look at the dual space, at the dual projective space, the projectivization of the dual vector space V dual. So this is a summary of this first step. So we project X to Y, And then dually, we have the dual projective space, we have the isomorphism of the dual space, so we can consider the same thing, the total space of the cotangent bundle of this P of V star. So with the same description, and we may project it also to this endomorphism of V star, and we get a singular variety, Y prime, with one singular point at the origin. But then, so this space Y prime is isomorphic to Y via the isomorphism that just maps the matrix to its transpose, basically. So you take an endomorphism of V, you send it to its dual, and this identifies Y with Y prime. So the results of these two constructions are actually isomorphic. And so that is how these variational transformations constructed. So we first construct the zero section, and then we use a blow-up by a different construction. So if we compose these two maps, we get some rational map going from X to X prime, going from the total space of the cotangent bundle of P of V to the total space of the cotangent bundle of P of V dual. So explicitly, this map, mu, the rational map, is just the following. So using my description, we have a point in the projective space, and this matrix that gives a cotangent vector, and we map it to a point in the dual projective space. So this point is a hyperplane in P of V, and the hyperplane is given by the kernel of this matrix. So the matrix is of rank 1, generically. So its kernel is a hyperplane, so that it's a point of the dual projective space. And as the second coordinate, we plug here as a transposed matrix, basically. So this is from arbitrary dimensions. This is only a rational map. So I have started from the variety. So here V was K plus 1 dimensional. So when K is equal to 1, then actually this map extends to a regular isomorphism. From the cotangent bundle of the projective line to the cotangent bundle of the dual projective line, we actually get an isomorphism here. But in higher dimensions, so starting from P2, this map is not regular anymore. So this is really a birational transformation whose indeterminacy locus is the zero section of this total space of the cotangent bundle. So this is a basic example, which is also a local model. So now let's talk about how to use this as a local model, actually.
Does it depend on you?
On U, sorry, what does not depend on U?
This mu, the map. Because the other side seems to depend only on the matrix.
So this matrix is inside, so this
The
dependence.
matrix depends on you.
Yes. So this pair, this A is not independent of U, right? So yeah, the dependence is here.
And what is the degeneracy locus again?
So the indeterminacy locus is just the zero section of this cotangent bundle. So it's a Lagrangian subvariety, right? So this cotangent bundle has a symplectic form, and this zero section is the projective space itself embedded there. It's a Lagrangian subvariety for the symplectic form. Well, actually, the end will always be Lagrangian because there is no homomorphic two forms. So it is half-dimensional, so you first contract it and then you blow up somehow, then you use the inverse of the contraction from the dual space. Okay? Right, so here are more questions. Right, so now how to use it as a local model. So local model, I want just to use a small neighborhood of this zero section in the cotangent bundle as a local model. So to get this small neighborhood, I just look at this Y. So this Y is a singular affine variety. So it has one singular point. I may just, so this is this diagram. And now I may just take a small ball inside of this affine space around 0 and take the intersection of this Y with this small ball. So this will be some open subset of Y, and I take its pre-image on the left hand side and on the right hand side. So this is somehow a small local model of this Mukai flow, but then also I want to take a product of this local thing with a disk or a polydisk. So so this is my small neighborhood of zero in this inter-Morphism space, and then I take a product of this whole diagram with a polydisk of some dimension, arbitrary dimension d. Yeah, so then so this becomes, so I just formally add some dimensions by taking the product of this previous diagram with some germ of some smooth manifold of dimension d. So I would like to use, so this will be my local model of Mukai flow or Mukai's elementary transformation. So the singularities of this u times delta d are smooth. So the singular locus, so this is just 0 times delta d. So what this map does, it contracts a pk bundle over delta d, and that blows up another pk bundle in a different direction. So my local model of the transformation is that I have some variety inside of my space, which is a pk vibration over something smooth. So then I contract this pk vibration and I blow up in a different direction. So let's give a name to such transformation. So if I have a bimorphic map between complex manifolds, then I will say that this phi is Mukai's elementary transformation in codimension k. Yeah. If this phi is, if there is a diagram of the following form, if we have two contractions p and p prime, prop small hypermorphic contraction, so prop is clear, so that the files are compact. Small means that they do not contract divisors, these contractions. And this n is singular, but the singularity of n is of this special form. So for every singular point in n, I can find some small neighborhood of this point, which is isomorphic to u times delta d of the previous slide.
And in any instance, this can be thought of like some sort of Fourier Mukai transform.
Fourier Mukai transform, well, I guess it's actually more basic maybe than the Fourier Mukai transform, because the Fourier Mukai transform will be for derived categories, and this is some basic geometric experience.
Like you have the differential forms, then you do like a correspondence bundle, you integrate all the fibers of one.
Yeah. So you may right. So to define the Fourier Mukai transform, what you may do, you may kind of use another diagram. You may first blow up this zero section and then blow it up. So you would have a diagram with different shape a little bit, but very similar. It will be so this birational map, and then you blow up. So you have some Q here, and then you blow down. And then to define the Fourier Mukai transform, you first pull back whatever you want to for homology or derived category, and then you push forward. Okay. So the advantage here is that you don't have to pass to a singular variety. But for me, it will be a bit more easy to talk about contractions than
But what
blocks.
will be usually you pull back, you multiply by some
variables and then push forward.
what do you use to multiply?
Oh no, I don't use it. I don't use anything, but it just was a question about Fourier Mukai transforms.
Yeah, but what we can use for Fourier Mukai if you want to do it here?
I mean, in the simplest case, you don't use anything. You just pull back and then push forward, or you can take some convolution to some kernel.
Yeah, this is what my...
No, I think that then, I mean, somehow the basic is that you just pull back and then push forward.
That's what they're for.
Is M prime a modular space of something on M?
No, so I don't need anything, any such, no. It's not a modulus, no, it's nothing. So it just is, if I have just two complex manifolds, not even projected, nothing. So the important thing is that the first, so this phi can be decomposed into two steps. So first one is a contraction,
which needs to be proper. So proper is important here, so that you contrast all the fibers are projective spaces of dimension k. Okay. Fibers are projective spaces of dimension k. And then, locally around each point, so this n will be singular necessarily because you have constructed something that is of a dimension bigger than 1. So this n will become singular necessarily. But then around every singular point you have a local description of this diagram. If you restrict to a neighborhood of this singular point, then this neighborhood is isomorphic to this previous picture. And if I pull back this neighborhood, then this diagram becomes isomorphic to the diagram on the previous slide. So to this one, this diagram. Okay. So that's just a local picture. And in particular, it means that this n singular is smooth. So this n is singular, but not too singular. So the singular locus itself is a smooth manifold. Okay, so now, so why do I want to consider such transformations? Actually, one may hope somehow that, well, maybe one may ask if this transformation is universal in some sense. If I consider arbitrary meromorphic map or birational map between projective manifolds, hyperkähler manifolds, for example, or manifolds with trivial canonical bundle, simply. Well, maybe I can decompose every such birational map into a composition of something that looks like a Mukai flow, like this Mukai elementary transformation. It's not actually true. Well, that's, so this transformation is very special. So this singularities of n, the single locus is smooth. So this picture is very, very, very special. You may construct non-trivial examples of such Mukai elementary transformations, but they will somehow the life or so the transformations that appear naturally are more complicated. And yet, somehow there was a conjecture that to a certain extent, one should be able to say something about the possibility to decompose any bimeromorphic map between hyperkähler manifolds, for example. Let's talk specifically about hyperkähler manifolds now. So Hu and Yao suggested that actually one may decompose this intercomposition of Mukai's elementary transformations, but up to removing something from M and M prime, up to removing something of the dimension higher than 2. So this transformation, this Mukai's elementary transformation, so the smallest codimension when I can do it is 2. So I can blow down some subvariety of codimension 2, which is a P2 fibration over something smooth, and then blow up. So the minimal possible codimension is 2. Codimension 1 not possible because I cannot construct devices. I'm not allowed to construct devices because of the canonical bundle. And so somehow the suggestion was that this codimension 2 thing you can control to a certain extent. You can say that if you remove, so you can somehow take the conjecture was stated midway. So to formalize it, let's introduce some other definition. So let's say that, just to formalize what we want to do. So let's say that a bimeromorphic map between two complex manifolds is a Hu-Yao transformation, so after the hypothesis of this conjecture. If the following holds, if there is two subvariations, closed subvariations Z and Z prime in M and M prime of a dimension 3 or greater, such that if we throw them out, this Z and Z prime, then what remains, this psi will induce by a meromorphic map from M minus Z to M prime minus Z prime, and this is actually Mukai's elementary transformation in codimension 2. Okay, so that is what should be a basic building block according to this conjecture for arbitrary bimeromorphic transformations between hyperkähler manifolds.
What was the context where this conjecture was posed?
Context? Well, I mean, it was in the paper, so it was specifically dedicated to the study of this bimeromorphic because people wanted to understand, you know, birational geometry of Calabi-Yaos in general, not only, actually maybe even the Hu-Yao, even we're talking about simplex manifolds more generally, and even maybe Calabi-Yao, no, I think that simplex. But in general, you want to understand how the bimeramorphic maps between Calabi-Yau manifolds, what they are. Yeah, to give some more or less good description of them. In the well, for example, yeah, so there are lots of natural questions that arise there. So what you can say about bimeramorphic Calabi-Yau?
Should be compared to conical constructs.
Yeah, so for Calabi-Yau, yeah, it's when you talk about the conical transforms. Yeah, so there are lots of natural conjectures there. So this was one kind of natural suggestion because basically, so this is the most basic type of this Mukai flow is the most basic type of the transformation that will happen. In all the examples that we were able to consider, it looked like, at least in dimension 2, this always looks at as a Mukai flow.
So conical transition is always composition?
No, okay, so the conical, I guess, maybe I'm not actually a good person to ask about the conical transition, so at least now I'm not sure. So no, I wouldn't say that.
There's a common framework in which this is the special case of conical transition and the conical transition is the special case of conical transition. You can do it versus general, I can tell you.
Okay.
Yeah, so this is, the conical is more for the Calabi-Yau of the type that did not actually have symplectic forms. Okay? So this is more, so let's just for now talk about this symplectic feature. So this is more related to the symplectic feature. And okay, so what was known about this conjecture? Actually, the conjecture was proven about already more than 20 years ago in dimension 4. And even something stronger than this conjecture was proven. This was the work of Wilsbach and Wisniewski. So they proved the following thing. So first, so they have studied the symplectic manifolds of dimension 4, and they have studied their small contractions. So again, small means that this contraction does not contract divisors. So they have considered the case when this small contraction, so this small contraction should be the first step in this bimeramorphic mechanism. So they have basically worked in the projective context, so they have considered the case when the result of the contraction is quasi-projective. Well, then you may actually support the term is also quasi-projective, so this is not maybe so important also. But anyway, so they have studied this situation. What they proved, actually, generalizing some previous works of Kawamata, is that any such small contraction from a symplectic manifold of dimension 4 to M has, as an exceptional locus, as an exceptional set, has just the disjoint union of several copies of CP2s. So this is exactly this first step of the Mukai flow, right? So for the dimension of 4, if we want to consider Mukai flow in dimension 2, then it should be just a contraction of CP2. The CP2 which sits inside of its own cotangent bundle as a zero section. And this is also true here, yeah, so that locally this pi is exactly, so locally analytically every such CP2 inside M will have a neighborhood that is isomorphic as a symplectic manifold to the neighborhood of the zero section in the total space of the cotangent bundle of CP2. So this is exactly this local feature that I have shown before. Alright, and from here, well, one can deduce this statement, this Huyao conjecture. Basically, so if we know that all the contractions are of this form, then Wilsbach and Wisniewski, they argued as follows. So they used some arguments from MMP to state, to claim that any such map actually can be decomposed into a finite sequence of flows. So this used MMP, that was available already at that time, and then every flow, so every flow is a sequence of a contraction and a blow-up, and the contractions are of this special case, so the exceptional locus of the contraction is CP2, and so all these flows are the standard Mukai flows in this sequence. So using this MMP argument, they were able to conclude that actually we have this statement of Huyao conjecture even stronger. So in this case, in the case of dimension 4, we do not have to remove anything of codimension greater than 2, neither from M this is very special for this dimension 4 Kelly manifold. So this meromorphic map or birational map between M and M prime. So Rodrigues worked in the projective setting basically. So they actually assumed that the M and M prime were projective. And then in this case it's just a sequence of blowdowns of CP2s and blowups of CP2s. And then, okay, so there's a question about this general case of the Fouillard conjecture remain open, but now we have a better understanding of the somehow of the birational geometry of Kelly manifolds of arbitrary dimension, and we have some wall crossing picture to describe actually such bimeromorphic maps, which we understand much better now. And so our approach that we use is a bit different, our approach to this conjecture. So we don't use MMP, but instead we rely on our better understanding of the wall and chamber structure of the, which I will explain next. But first, so before I pass to this explanation, so let me state actually the result that we prove. So I have placed here again this definition just to recall. So again, so a basic type of a birational transformation for us is a Fouillard transformation, which is the following thing. So I remove from M something of big codimension, from M prime also something of big codimension, and then on the complement this psi is a Mukai flop, basically Mukai elementary transformation.
These are volume preserving.
Sorry?
Some volume preserving transformations.
Preserving? I didn't want to volume.
Yeah, it preserves homogeneity form.
Oh yeah, so for high-Kelly manifolds, yeah, so there is only one form, so this transformation has to preserve it automatically, right? In general, for the definition, I don't require this, but in our context, it will be true. So the theorem is the following. So if we have two compact Kelly manifolds and then bimeromorphic map that is not regular in codimension 2, okay, so this is the case which we can study when there is some indeterminacy locus in codimension 2, because if there is no such locus, then this Fouillard conjecture does not say anything about it.
It's true.
Yeah, it's true, because you can claim that somehow you can just, if the indeterminacy locus is of high codimension, then by the conjecture we can just throw it out, and what remains is a regular map. So we cannot say anything about such bimeromorphic maps that are regular in codimension 2. So we assume it is not regular in codimension 2, but then we claim that this phi is a composition of such elementary transformations, Fouillard transformations. So at each step I may throw out something of codimension 3 and higher, and then blow down this P2 bundle, blow up the P2 bundle in a different direction, and then go on. Again, removing something of high codimension, and blowing down and blowing up. Okay, so then, so now so what's the idea of the proof? So how much time should I have?
Like 10 minutes?
10 minutes, okay, so I'll go a bit fast. So the idea is that the wall crossing picture, as I said, so what kind of wall crossing, so where are these walls? So to describe birational transformations of Kelly manifolds, we want to look at the Kelly cones. So we have the cohomology, and this cohomology has some bilinear form, non-degenerate bilinear form of this signature. So if you are more familiar with K3 surfaces, you may just think that this Q is a generalization of the intersection product of the second cohomology of the K3 surface. So this is an analog. So this bilinear form, if we restrict it to the one part, it will have this Florentin signature. And then we can consider the corresponding hyperbolic space, which is the projectivization of the positive cone in the space of this signature. So here is the positive cone, and inside of this positive cone there are Kelly classes of our manifold. This Kelly cone, the collection of Kelly classes, is an open subset inside of this cone Cn. So so the Cn is a connected component, it's a connected component of this cone that contains the parallel classes. Okay? So actually, the cone, this positive cone, has an interesting wall and chamber structure. So this was done previously by Tarde and Münch. So they have shown that there is a certain collection of topology classes called MBF classes that define a collection of walls in this positive cone. So the walls Wi. And so this wall, what is their meaning actually? The meaning is that so they divide the positive cone into some chambers. And the thing that we're going to use is that if we have a binary morphic map from M to a different hyperkähler manifold, then the pre-image of the Kähler cone will be one of the chambers in this wall and chamber decomposition. So the union of all such connected components, the union of all these chambers that are obtained this way is called a birational Kähler cone of this manifold M. And now, so what do we want to do now? So now, since we have this wall and chamber structure, we actually want to understand how to cross a wall. So, I'll show you a better picture a bit later. So we have these walls in the hyperbolic space. And then we want to pass from one chamber to some other chamber. So for example, there are two chambers here. So to pass from one chamber to the other chamber, we want first to understand what happens if we cross one wall. So one wall which is adjacent to the chamber where we see. So if we cross just one wall, this means that, so by neuromorphic map, what does it mean to cross a wall? Is that these Kähler cones of M and M prime share a common wall in this picture, for example. And then such binary-morphic map is called a wall crossing flow. And we proved that this wall crossing flow is also a special shape. It is a composition of a contraction and a blow-up, just as in the previous pictures. But the difference is that in general this contraction and blow-up may be a bit more complicated than in the Mukai flow. So this M may be more singular than what we had before. But anyway, so the first step is to decompose arbitrary binary morphic map between hyperkähler manifolds into a composition of such wall crossing transformations. So this is simple because Tarde and Münch have shown before that this wall's chamber structure is locally finite. So we have only finitely many walls in a neighborhood of every point of the hyperbolic space. So given two chambers, we always can connect them by a geodesic segment in the hyperbolic space, and this geodesic segment will cross only a finite number of walls, one wall at a time. And then we get a sequence of such binary morphic maps that are wall crossing flows. So actually, I wanted to give you an example at this point, just to be a little bit more concrete. So I don't think that I have too much time to spend on this example, but let's have a look quickly. So if you take, so what would be an interesting, non-trivial example of a hyperkähler variety with some interesting, non-trivial birational geometry? So if you start from a K3 surface, so you want to this K3 surface and then pass to a Hilbert scheme. You want this K3 surface to have some non-trivial Picard group. So Picard rank 1 is not very interesting because Picard rank 1 will give you M of Picard rank 2, and it is not maybe very rich in the sense of this wall and chamber structure. So the first interesting case is when this S has Picard rank 2 at least. So for example, let's take a quartic containing a line, a quartic containing a line in E3, and take its Hilbert scheme of 3 points. Hilbert scheme of 3 points on this, So what kind of classes do we have there on this K3 surface? If we consider a plane that passes through this line, contains the line C, then the intersection of any such plane and the quartic is a union of this line and then an elliptic curve. So these pencil planes that contain C, this pencil plane defines an elliptic fibration on our K3 surface, because fiber is an elliptic curve denoted by F. And then actually the Picard group for a generic quartic is of rank 2, so with some intersection matrix. And then when you pass to the Hilbert scheme, you add to the Picard group an additional class, which is a class of the diagonal of this resolution, not of the diagonal, of the exceptional divisor of this resolution of singularity. So this S3, the Hilbert scheme, is the resolution of the symmetric cube of S. So it has an exceptional divisor, and the class of this divisor divided by 2 gives an additional generator on the Picard group. Okay, so this class delta defines one of the walls in this wall and chamber structure. And there are actually more walls, so this picture is more interesting. So there are more walls, so let me just show you the picture. So this big thing, so the thing here is the birational ample cone. So this is the intersection of the birational Keller cone with the subspace spanned by the neuron serrated group. So just to reduce the dimension, I take the intersection with the neuron serrated group, then I get a hyperbolic space of dimension 2. And there, in this space, I have some complicated wall and chamber structure. So my Hilbert scheme, so this somehow the lines, these geodesics are the walls. They have different colors. The color here depends on some numerical properties of these walls. But so the spaces between these walls are the chambers. So there are 4 chambers with numbers here. So the chamber that corresponds to the Keller cone of this S3 is actually number 3 in this picture. And there are more walls. So this delta, the class delta, the orthogonal complement to delta defines one of the walls. It's here. And there are more walls that are listed in this picture. Well, just let me mention briefly that, these walls are very explicit. Here you can compute. For example, you have this rational curve on your K3 surface. You may consider the collection of the triples of points that lie on C, or the symmetric cube of a rational curve. The symmetric cube of a rational curve is P3. And this P3 defines some locus in your Hilbert scheme. So this locus is actually listed here. So the corresponding rational curve on this locus defines another wall that is called gamma. So the orthogonal complement to the class of this rational curve defines a wall gamma, and then in this picture the gamma is here. So what you can do these flops. So in particular, so if you want, for example, to pass from chamber 3 to chamber 2, then you do the flop in this P3. Then you may pass further to chamber 1, and for this you need to make a flop in the wall called beta. And beta is described here. So this beta is the closure of the set of points in the Hilbert scheme, so that the 2 points lie on the curve C, and the 3rd point is arbitrary. So there is this locus, it is of codimension 2. And this flop is kind of the flop of codimension 2 that we are interested in. So this is just an example of this wall and chamber structure that you can compute explicitly to have a look at what happens with your biomorphic transformations. So now, to conclude this story, so now we have decomposed everything into a sequence of wall crossing flops. So now how do we actually conclude the proof of the Weyl conjecture? We need to prove that this wall crossing flop is actually a Weyl transformation. That is, we may remove something from M and remove something from M prime of high codimension in such a way that this becomes isomorphic locally to this local model. Well, I mean, there are some technicalities which I don't want to describe in great detail, but so first thing is that we do this in general for arbitrary hypercadence, and it is to use some of the tools that we need to know how to deform these things. So we have a very good deformation theory for hypercad manifolds and for singular symplectic varieties. So we can always deform this whole diagram in such a way that everything becomes projective actually. So this is based on the results of Becker and Len about locally trivial deformation. So locally trivial means that the deformations preserve the structure of the singularities and the contraction centers. And then after we deformed everything to become projective, we look at this N. So this is a symplectic variety, singular symplectic variety. So if we have a singular symplectic variety, then there is a theorem of Kaledin that tells us that there is actually a stratification of this M. So you can cut this M into locally closed sub-manifolds that are also symplectic. So the open stratum is obviously just a smooth locus of N. The smooth locus of N carries a symplectic form. Then if we look at the singular locus of N, we can stratify it further. We can take the singular locus of the singular locus and then go deeper and deeper along this, to the deeper strata. And actually the statement is that every of these smooth strata there is a symplectic form. So all these smooth strata are even dimensional, for example, in particular. And they have symplectic form, and all these symplectic structures they glue together into some nice Poisson structure, and actually which you can use. So then, so what we want is to consider the somehow the strata of the minimal possible codimension in M.
So this is holomorphically symplectic?
Yes, it is holomorphically symplectic. Everything is holomorphically symplectic, right? So we want to look at the stratum of the singular locus of N of minimal possible codimension. And the minimal possible codimension will be 4 in this case, because we have contracted something of codimension 2 along a P2 fibration. So the result will be of codimension 4 in N. So if we have this stratum of codimension 4 and we have a point there, and then using the results of Kaledin and use this Poisson structure on N, we can construct some transverse, we can cut this N transversely to the stratum. So the picture is something like that. So we have this stratum N prime of codimension 4, and our N is it is singular along this stratum. So it is actually something like that. So we have some two things intersecting here. Along this stratum. So this is a stratum and this is a point here, X. And then what I am saying is that I can cut somehow all this thing transversely to the stratum, so that the intersection, so this intersection of N with this slice is, so this slice is a symplectic sub-variety of N. So it passes through this point. It is transversal to N prime. It has a symplectic form. It is also singular, but it has a symplectic structure. And then what is this? What is the dimension? It is of dimension 4, right? Because N prime was of codimension 4. So this S is now, if we do it carefully, then we can guarantee that this S is actually quasi-projected. And then we're in the situation where we can apply Rodrigues, because this S now is a fourfold. And if we look at this pre-image, then this pre-image is a smooth manifold, a pre-image under P, for example. And then we get a small contraction from one symplectic fourfold to the singular symplectic slice. And we can use Rodrigues, apply Rodrigues here, and deduce from there that the exceptional set of this contraction is CP2. And then this way, so doing this for arbitrary point in this stratum N prime, we conclude that this P at this N prime is a contraction of a P2 bundle, which is exactly what we want, because what we want is to prove that there is this local isomorphism with this Münch flow, which is exactly a contraction of the P2 bundle. So Münch flow, good dimension 2. So analogously for P prime, we can do the same thing and then conclude that actually locally around each point, so this diagram is locally isomorphic to this standard local model of Münch elementary transformation, and then this completes basically the proof. Okay, so I think I'll stop here. Thank you.
Let's think and begin. And we continue in 5 minutes with Pedro. All right, guys, let's start. So now we continue with Beatriz Brienda from IMPA that's going to talk about holonomy of the water connection on joint hypercomplex methods.
So thank you very much for the invitation. Thank you very much for being here at the fifth talk of the day, of the afternoon. So this is a joint work with Uda Foda, Zoran Gentili, and Luigi Pizzoni. So I say this in advance in case I forgot. And we try to address this problem about the holonomy of the water connection, which is a special torsion-free connection that arises in hypercomplex geometry, on a special class of hypercomplex manifolds called joint hypercomplex manifolds. So to give a bit of motivation, probably I want to give some history about irreducible holonomies of torsion-free connection. And the first theorem that I hope everybody has in mind is the theorem of Rodrigues. So the idea is that if we have a complete, oriented, and simply connected Riemannian manifold, and we exclude two cases. So we exclude that our manifold is a product of lower dimensional Riemannian manifolds, because in this case the holonomic group is going to split. So we can just focus on only one factor. And we assume that this factor is not locally symmetric, because this case has been completely addressed by time. Then the Brigitte theorem tells us that the Riemannian holonomic group, which is the holonomic group of the rigidity connection, is one of the groups in the listing group. So from a very simple object, which is the Riemannian holonomic group, I detect information on the geometry and the topology of my manifold. For me, this theorem is kind of amazing, and actually, when this theorem was wrote, it was 1955, this was a list of possible irreducible Riemannian holonomies. And just let me state once for all that by irreducible, I mean that there not exists any subbundle of the tangent bundle which is preserved by the connection. And this was a list of possible irreducible Riemannian holonomies because, for instance, examples of Riemannian manifolds with holonomy G2 and spin 7 were not known. They were found kind of 30 years later by Bryant and so on. So starting from this theorem, which can be an upward generalization. I mean, Riemannian case is close to this theorem, it's completely understood. So the first idea could be, okay, instead of considering the rigidity connection that is both metric and torsion-free, I can consider just torsion-free connections. So I do not assume any compatibility with the Riemannian metric from the line Riemannian metric. And actually, this was the idea in the same paper of Berger. In fact, here I'm cheating a little bit. The Berger paper was kind of divided into parts. In the first part, he classified all the possible irreducible holonomic group of torsion-free connection that preserve a symmetric non-degenerate linear form. Here, I'm setting the term for signature N0 for Riemannian metric. But in general, the classification holds, of course, we have many groups over here, even when the signature is not the good one, it's not N0, right? And in the second part of the same paper, what Berger did is try to classify all the possible irreducible holonomic groups for torsion-free connection without any metric assumption. However, the list of Berger was not complete. A finite number of entries were missing in this list. Nowadays, we have the complete classification due to Merkur. Actually, also their list was not completed, and was completed a couple of years later, if I remember correctly, by Robert Bryant. This is the idea, so this is a bit of history. So what about the Watt connection? Well, the Watt connection is holonomy perfectly fits in this scenario. And for me, this is a great motivation because it's a very historical problem to study holonomic groups of torsion-free connection. So to introduce the Watt connection, I have to go a bit in hypercomplex geometry. I don't need much about hypercomplex geometry in general, so I will try to be fast. But if there is something that I'm missing or something that I'm not explaining at my best, please stop. So, okay, what is the idea? The setting is the setting of a smooth manifold. And we assume that our manifold is endowed with a triple complex structure, IJK, we saw this in previous talk, that satisfy the multi-quaternion relation. Meaning that I and J are equal mute, and this is equal to K. And the same must hold for any cyclic permutation. In particular, this force the dimension of the manifold, the real one, to be a multiple form. Nice.
So what is the example of every K3 which is not careless?
If I recompensated again. Perfect. And whenever you have my manifold and it's endowed with structure, how about call this an hypercomplex manifold? This is an example, HN. So if I consider the hypercomplex structure on HN induced by the imaginary units I, J, K, this is an hypercomplex manifold. Now, which is the problem in hypercomplex geometry, let's say? So we all know that by Nylander and Dynamical theorem, that if I fix one complex structure, so if I fix L to be N, I, J, or K, I know that my manifold is locally modeled over C2N without which resemble the imaginary unit type, so the square root of -1. So the question would be, does this behavior unify when I consider I, J, K together? Is my manifold locally HN with a standard hypercomplex structure? The answer, fortunately, is no. So in general, a continuity version of the Nylander and Dynamical theorem do not hold. So we cannot dualize, let's say, much of local theory with coordinates in hypercomplex manifolds. However, this condition is true whenever the Obata connection satisfies some very good properties, as for instance, when it is Obata flat.
But this proof is not PDE, right? Or like this isomorphism in the case of Obata flat.
Sorry?
Is like a PDE proof in this case of the Obata
You know
flat?
that, Misha, do you know?
No, it's not PDE proof. It's very simple differential geometry. The idea is that graph of hypercomplex map is totally geodesic with respect to Obata.
Okay. Nice.
Thank you for the question. Thank you, Misha. So let me introduce the Obata connection. So this is a theorem of Obata back in the 50s, which states that if I have an hypercomplex manifold on this tangent bundle, I have the existence and a uniqueness of a torsion-free connection, which I will call this nabla from now on, which is always the Obata connection, that preserve I, J, and K. So I'm asking that nabla L is equal to 0, where L is 1. As I told you, the condition that these guys are actually locally isomorphic is equivalent to us that the Obata connection is flat, meaning that it's restricted or unrestricted. So examples. Of course, by this characterization, if I take Chen, this is going to be Obata flat. It's locally isomorphic to itself. Many examples of Obata flat manifolds actually arise in hypercomplex Neal manifold. So by hypercomplex manifold, I mean a Neal manifold endowed with a left invariant hypercomplex structure. Some of them are actually Obata flat, especially in the two-step case. A third example is given by the X-surface. So the X-surface can be constructed as we take quaternions minus 0, equiquotient by the action of a 0 quaternion with a suitable norm. The hypercomplex structure here is induced by the 1 which H minus 0. So it's of course locally isomorphic to H. We all know that, the surface is diffeomorphic to S2 times S1, and it is Obata flat by this criterion here. Also, this is the lowest case of a choice hypercomplex manifold. We're going to see in a moment what these guys are. So let's do a bit of Dynamic. So by the Dynamic principle, we know that nabla preserved by JK. This means that its Dynamic group is always contained in GL and H. This could be a problem because, the Dynamic group is not compact in general. So we cannot really use the theory that we are used to, let's say, for Riemannian lines. We have to do, let's say, we have to put more effort somehow. And since, I told you that there is a list of possible irreducible Dynamic group of torsion-free connections, one can look at the list of Mercury-Schaff and see, okay, which subgroups of GL and H appear in that list? Actually, only 3, not many. So we have SPM, SLNH, and GLNH. So the first group is probably the group we are more familiar with. So we have the autonomy of the Obata connection is contained as SPN, if and only if there exists a metric for which this term is actually ever clear. So what I'm saying here is that the autonomy of the data connection is inside SPN if and only if the data connection is the legitimate connection of an hyper-emission metric. Because in this case, OData and legitimate are going to coincide. So we go back to the classical and Berger case. The second example is given by SLNH. SLNH can be defined as a commutator of GLNH. And we have actually many examples of hypercomplex manifold with autonomy inside SLNH. Let me cite this theorem. So it is a very well-known result of Barberisdot and Verbitsky that whenever we have an hypercomplex manifold, then we know that the autonomy of the data connection is always inside SLNH. So at least for these two cases, we have plenty of examples, right? Like, okay, we have hypercator and at least any hypercomplex manifold. But actually, the most mysterious case is the case with full autonomy. Because actually, we don't have many examples with hypercomplex manifold with full autonomy. The first example was found by Florentin in 2011, who proved that if we take the C3 and we consider any left invariant hypercomplex structure, then the autonomy is going to be full. This was really a groundbreaking result in the literature because, it is really the first example in literature of a manifold hypercomplex one with autonomy GLNH. And it has been an isolated example since this paper we were able to find another example. Okay.
So,
please.
So, I'm not sure if I understand this correctly. The notion of locally isomorphic in the quaternionic case. For complexes, it means locally biholomorphic, right? So
yeah, exactly.
Quaternionic, you want it to be quaternionic holomorphic?
Yeah, kind of, exactly.
Okay.
So there exists an atlas, usual definition. I'm using locally isomorphic to be a bit fast. But
Okay.
it's precisely the existence of an atlas and so on.
Okay, guys.
Thank you very much. And this is the second example of a joint hypercomplex manifold that we encounter today. So okay, now we're going to define what these guys are. So the construction of joints is not complicated. It's a bit technical, I have to say. So I will try to skip all the boring details and I will try to make you understand the philosophy or the idea behind it. But at the very beginning, we need to do not hypercomplex geometry, but just joint decomposition of Lie algebras of complex semi-simple group. So at the moment, we just go out from the hypercomplex realm and focus in the case of G to be any complex semi-simple group. We know that inside of G, I can pick a maximal torus. This is not unique, I can always do this. And I will denote with little letters the Lie algebras. For me, now on, R is always the rank of the Lie group. And the last ingredient that I need is a system of ordered groups. So, just to recap. Complex semi-simple group. I have a maximal torus, I have its rank, of course, and I fix a system of ordered groups. Why I'm doing this? So the idea is that starting from this ingredient, I can build an iterative procedure to completely decompose my Lie algebra G. In which way? So, step one. We pick a maximal positive root. If the group is not simple, this is not unique, but we don't really care. And the idea is that this maximal root allows me to have a copy of SL2C inside a complexified Lie algebra. So the idea is just to take delta 1 tilde to be G alpha, G minus alpha in the bracket, which lies in the maximum torus. This is a copy of SL2C. Now, I intersect this copy of SL2C with G, and I get a copy of SU2. This is my delta 1, and it's everything I need to do the decomposition. In fact, if I consider my Lie algebra, then delta 1 induces the decomposition of G in 3 samples. Delta 1, C1, and F1. Delta 1 is the copy of SU2 that we have just produced using the maximum root. C1 is the centralizer of delta 1. So it's the vector fields in my Lie algebra that commute with any vector fields in delta 1. And then I have F1, which is a complement. It's actually one precise complement because it's the orthogonal complement of delta 1 plus C1 with respect to the Killing carbon 4. But again, we don't really care. Just keep in mind that we start from a compass semi-simple group with the maximal powers in a system of ordered groups. Now, picking a maximal root induces the decomposition of the algebra in three summations. The first is a copy of SU2, which corresponds to the copy of SL2C reduced by maximal root. Then I have the centralizer and the complement of 1. Why this is an entirely procedure? Because C1 can be decomposed in two guys. G1, which is the algebra of compass semi-simple group, and B, which is just B1, which is just a billion. So I forget about the billion part and reapply step 1 to G1. So which is the idea? The idea is that I start with G. I have my first layer of the decomposition, delta 1, C1, delta 1. Then my C1 is something a billion plus G1. And then I decompose again G1, which will be delta 2, C2, and F2. Again, C2 is going to be something a billion, plus again the algebra for compass semi-simple group, and so on. So in each layer of my decomposition, I reapply this technique. This inductive process is going to stop at some point whenever I get a centralizer, which is only a billion. So at the end of the day, what I want to say is that I have a complete decomposition of my algebra in three types of summas. I have B, which is a billion, so I'm putting together all the billion components that I got in each step. Then I have a bunch of copies of SU2, which correspond to these delta J's, and a bunch of complements. I will not go into the details of all the properties, but just keep in mind that B is a billion, and the dimension is, I always forget, R-7. Delta J's are copies of SU2. Both of them are lists of algebra. They have some nice relation in the sense that we commute with delta J, they commute if they are not equal, but again, we don't really care. The thing we care about is that if we consider the complement for each J, the dimension of the complement now is a multiple of 4. So let me call this 4kj, where kj could be 0. And now, the idea is that if I regard fj as c to kj, I have the prescribed action of delta I, so delta j and fj. So if I consider the bracket of delta j and fj, this is going to be inside of delta fj, and the action is prescribed in such a way that this action is exactly the action of SU2 on C to kj diagonally left. So we have a standard action of SU2 on C2, right? I have a bunch of copies of C2. In this case, I have actually kj copies. And what I'm doing is acting on each copy diagonally with SU2. And this is isomorphic to this action that I have here. This is kind of important for us, because this will give their complex structure later. So this is my decomposition. Again, could seem a bit technical. So at least for me, it's kind of good to look at examples. Let me say this thing now. So in order to get this decomposition, I make many choices. So for instance, I pick a maximal root, a system of ordered roots, and in each step, I'm fixing a maximal positive root, which is in general not me. However, if I make different choices, I will end up with a decomposition which is not the same, but always isomorphic. That's why I don't really care about all the choices that I made. So let's do one example. I will do SP2, which I really like. So we have to decompose it to the algebra. So from the algebra point of view, SP2 is given by quaternion matrices of order 2, for which if I consider A plus the conjugate transpose, this is going to be equal to 0, where the conjugate means the quaternion conjugate. So if I consider any element inside this algebra, I can always write this element with two diagonal terms, x and z, which are imaginary covariant, and one, let's say, off diagonal term, which is y, which is simple covariant. From this decomposition, it's kind of clear here, which is going to be, this is kind of encodes already the joystick composition. In fact, delta 1 is going to be my matrices of the kind x0, 0, 0. X is an imaginary quaternion, so this is isomorphic to SU2. Same thing for delta 2, when I say I'm considering 0, 0, 0, Z. F1 now is given by the off-diagonal term, and as you may see, this is a quaternion, so it has dimension 4. Why? In this case, F2 is trivial. As I told you, my Fj can be always trivial. I don't need that they are different from 0. Okay, nice. But there is another way to describe this, because, for SU2, the macro description is kind of easy. But if I consider a simple group, maybe it's not that easy, and it's very complicated to understand the joystick composition just from the macro's point of view. So, another technique could be using the so-called color linking diagrams. So, as far as I know, they were introduced by Renata Possobon in 1998. This paper was never published, but this part is correct, as far as I know. And used this colored fashion version of linking diagrams adapted to the joystick composition. So let us consider SPIN2. The linking diagram is this one, right? But instead of considering the standard linking diagram, I consider the colored one. What does it mean? It means that I have an additional root, which represents the maximum root. Not really important for what we're going to do. But the important thing is that my linking diagram has some color and uncolored dots. Why this color? Because as you see, in order to produce my joystick composition, in each layer, I have to understand which is the centralizer. I can't move in the next step if I don't know which is the centralizer, right? For kind of this, right? In each step, I have to understand the centralizer and the composability. So the color is really adapted on the joystick composition. In fact, the first layer, I'm going to have delta 1 F1 and C1. But which is the centralizer is precisely the color subdiagram. In fact, in this case, C1 is just one dot, which is SU2. So if the composition is trivial, it's just delta 2. So that's why I get the exact same decomposition using another technique, right? And this is particularly useful in area dimension. In fact, let me do quickly SPK. So, SPK, this is the linking diagram. Again, I want to consider the color linking diagram. So I'm adding an additional root and coloring the root of the standard linking diagrams. First step of the decomposition, delta 1 F1 C1, which is C1, I have to look at the subdiagram which is colored. But in this case, the subdiagram which is colored is just the same diagram with just k minus 1 dots. So it is SPK minus 1. And again, I can decompose SPK minus 1 and obtain the whole decomposition of my algebra. And this applies for any simple group. It's very, we have fun doing this. Okay, except for, I'm not going to do this because otherwise I cannot finish the slides. Sorry, I don't know what I was doing there. Okay. Now, we have our decomposition. So now, we have to construct hypercomplex manifold. But, the dimension is not good, right? Because I pick any semi-simple group. For example, pick SU2. It has dimension 3. How can I build hypercomplex manifold? In India, is kind of multiply my group with a sort torus of a suitable dimension. And the dimension that I'm picking is precisely 12 minus r. And you're going to see in a moment why. So I brought this here. The dimension of B is r minus n. So if I put the abelian part together, this is going to be a billion of dimension n. Be careful. In order to do this identification, I need a basis. Otherwise, I'm not doing anything. I have to fix a basis to interpret this as a Copen format. And this basis is the only choice that really matters. If I change this basis, I will end up with other complex factors which are not the same. So this is the only choice we have to care about. But which is the idea now? Now we have n vectors here and then copies of SU2. And U1 plus SU2 is a Copen quaternion. So the other complex factor, at least on this part, is kind of natural. It is the standard one on each. Now let me fix a standard basis of SU2, and I use precisely this action to induce an hypercomplex factor in J. In fact, for F belonging to Fj, EF is going to be the action of E2J, JF the action of E3J, and KF the action of E4J. Now, so here, standard one, here I use this action of SU2. Now you have to do like an act of trust. This is integrable and it behaves very well. And this is called the Joyce hypercomplex factor since it was introduced by Joyce in 1992. Although it was not, there was, I believe, a paper which was some years before, which is the paper of Spin and other people, Fasich's paper, but I like to call this Joyce hypercomplex. And whenever you have torus mg and ijk constructed in this way, this is going to be a Joyce hypercomplex manifold. If you are lost, just keep in mind that has been proven some years later by Dimitrov and Sanov and Viduli stuff that Joyce hypercomplex manifolds are nothing else than a completely group and with left invariant hypercomplex structure. Okay? So if you have only group, compact, and it has a left invariant hypercomplex structure, the hypercomplex structure is constructed in this way. With a suitable choice of these bases, right? Now, I started with a compact semi-simply group, but I became clever and look for simply groups. So in order to understand which manifold can admit this structure, I have to count the dimension of the torus, which depends on the rank of the group, and then, which is the Joyce decomposition of my group. But that was somebody did for us. This is the work of Spindler and other people. And what they did is just counting the dimension of the torus for each simply group. Now, in dimension 4, we have the surface. But I told you, this is about the flat. So, kind of easy. In dimension 8, the only example is SU3. And we have seen that the autonomy for any hypercomplex structure that I consider any Joyce hypercomplex structure is GL2H. How so that I can prove this? Maybe I can tell you, but okay. The proof is divided in two steps. In the first step, he proved that the autonomy of the beta connection is irreducible. Then he appealed to the Merkur-Stoffel list. We know that the autonomy can be only SP2, SL2H, and GL2H. And the last part of the proof is just rule out SP2 and SL2H. When we got interested in this problem, why got interested in this problem? Because it was this Volcker conjecture that if you pick a manifold in this list with an hypercomplex structure which is a Joyce one, then the autonomy was going to be full, inspired by this example in dimension 8. Always we exclude the surface because this is quaternionic dimension 1, so it's kind of a trivial case. And I believe it was common to believe that this conjecture was true. And when we got interested in this problem, it was me, Uda and Giovanni at some conference, and we said, okay, we should do something together. And so that's why we said, okay, let's solve the conjecture. Of course, we didn't solve anything. But the first idea was to try to generalize this proof for broader classes of manifolds. But we miserably failed in doing this. And actually, after some months, we discovered the reason. In fact, the Volcker conjecture was very far from being true. What we were able to prove that if we pick any Joyce hypercomplex manifold in the list, with the exception now for SU2K plus 1, which is precisely this case in dimension 8, then the autonomy can never be full. How we prove this? Actually, the proof it was like, we started from one example, we computed everything, and we tried to understand if this was possible in general for other class of groups, and then we saw that exactly was a criterion which allowed us to conclude this theorem. So let me fix the dimension of the manifold is greater or equal than 8. In dimension 4 we have the surface, this is about a flat, the autonomy is of course strictly contained in GLH. So we fix dimension greater than 8, greater or equal than 8, and we fix our manifold, right? So, which is the idea? The idea is that the Liager of this guy decomposing the Liager of the torus plus some part which corresponds to G. And again, I'm just rewriting in yellow the decomposition of G. As I told you before, everything is dependent on the choice of the basis, so the identification of the abelian part with some Rn by fixing the basis. And as I told you, the hypercompact structure is constructed by pairing each of these elements with the corresponding copy of SU2, because this gives us a copy of quaternions. Now, let me call this basis J, just for, it's useful for me. And let us just note that since it's a copy of quaternions, I can imagine this to be the quaternionic span of V1J, because any other is just I, J, or K of it, right? And I'm doing this in order to decompose my algebra in a nicer way, in such a way this is adapted to the hypercompact structure somehow. Because I'm putting things which go together, right? And I'm writing this as copies of Fj, which is copy of quaternions, and Fj's. Now we have a key lemma, which is basically the first step of our proof. We compute the connection of the data connection of V1J. And the idea is that if we evaluate this on X, this is going to be minus the identity if X belongs to Hj plus J and 0 that was. But this is a powerful thing, because if I have some indices for which this guy is trivial, then I have that the corresponding scope of H is preserved. Why? So let us consider the connection applied to V1J bar. Now, on each Hj, which is different from J bar, this is going to be equal to 0. And minus the identity on Fj bar. Now, since my Fj bar is 0, I have a bunch of zeros. So now the V1J bar belongs to Hj bar, right? Because the only place where something different is here, but this is minus identity. But then, the connection is hypercomplex, Hj bar is quaternionic, so Hj bar is completely preserved by the connection. But what does it imply? This implies that if I consider the corresponding left invariance bundle, this is parallel with respect to the web connection. And so, at the end of the day, my analogy cannot be full. Why? Let us pick a point of the manifold and pick a path, center that P. My five classical maps are going to preserve Hj bar. So, on Hj bar, I have something and a bunch of zeros. So, if I consider the set of all this map, this cannot act transitively on my tangent bundle. Because Hj bar has to remain in sub, I cannot move it, let's say. And so, if I have a trivial Fj summons, I have the dilemma that the web connection cannot be full. Now, why this criterion is kind of powerful? Because it's kind of paradox, right? We want to have information on the long web debug connection. But the fact that Fj is trivial is completely independent of hypercompact structure. It's only depending on the group. So this is why the theorem holds for any hypercompact structure, because this criterion is completely independent of it. Just depends on the geometry, on the joint decomposition of the simple group that I'm considering. So the last part of the proof is just look at each simple group and understand if it has a trivial Fj summons or not. This is the final list. And okay, you cannot read this like, sorry. But it's not really important. And as you may see, each of these groups has a trivial Fj summons, but SU2K plus 1 does not. So we get it here. How to understand if they have trivial Fj summons? We saw before the example of SPK, right? Let's do by induction. All these proofs are basically done by induction. So for k equal to 1, we can consider SP2, right? We saw it's the composition, F2 is going to be trivial. So allow me to reduce. Nice. Now we work by induction. So this is only the SPK case. Assume that SPK minus 1 as a trivial Fj summon. What about SPK? If you remember, SPK was decomposing as delta 1F1 and the centralizer. And the centralizer is SPK minus 1. Now, the joint decomposition, what we have to do is decompose SPK minus 1. And the decomposition of SPK minus 1, again by induction, is a bunch of copies of SU2 and a bunch of copies of Fj's. But by induction, reduction, at least one of these is trivial. So this will give me a trivial Fj summon in SPK. Is it clear? Somebody say yes, please? No. so what I'm saying is that in each decomposition of SPK, I'm reducing to the joint decomposition of SPK minus 1. And if this guy has some of these which are trivial, then also this guy will have. Because the Fj's of SPK will be F1 and the Fj's of SPK minus 1. More clear? Okay. I see faces so yeah, and basically all the other proofs are done in a similar way. How much time do we have?
10 minutes.
Amazing. Now, what about the last case? So what about SU2K plus 1? Because I've done everything but actually, okay? You know, we started from SU3, right? Was the case of Dynamical. And I mean, nobody investigated, I believe, all the other cases. Probably the SU2K plus 1 case is not the most interesting one. It's also the only one which is simply net. So what about SU2K plus 1? Okay, for SU3 we know any just hypercompact factor Dillon is full. What about K greater than 1? I will do everything for SU5, and you have to forgive me about this. But it's that things here became quite technical, sorry, and I don't want to go much into the details. I will rather to give you the idea. So let's look at the joint decomposition of SU5. So as before, what we can do today, delta 1 F1 and centralizer. Now the centralizer is a big difference here, because instead of having only a simple algebra, here you have the big part. In all the other cases, if you remember for SPK, the big part was always 0. Here, I have it. So what I'm saying is that from the joint decomposition, you see that there is a copy of SU3 inside SU5. So this is more formally the joint decomposition of SU5. So delta 1 is given by a copy of SU2 here. Delta 2 is a copy of SU2 there. And then I get my F1, F2, and the two abelian summons. E1, which is this one, and E2, which is inside SU3. In fact, sorry, I forgot to mention, SU3 has its own decomposition, which is just E2, delta 2, and F2. So, what I'm trying to say is that if I put these and these together, this is a copy of SU3. Now, as I told you before, my joint hypercompact structure depends on the choice of the basis of the abelian part. My abelian part now is spanned by E1 and E2. So I have to fix a basis of B, E1 and E1, which I can write with respect to capital E1 and capital E2. And just fixing up paper basis and saying all the other bases are just matrices of this kind with respect to the basis capital E1 and capital E2, right? Are we okay? So what we have is that joint hypercompact structures are parameterized by a 2x2 invertible matrix A. Okay, now. So what before, if you remember, I told you about the reduction of Delaunay. So the reduction of Delaunay was a linear independent joint hypercompact structure. It was holding for each of them. For SU2K plus 1, and in general for SU5, the situation becomes a bit subtle because the reduction of Delaunay will depend on the hypercompact structure dynamic sequence. So for instance, if I take IJK to be a matrix of this kind, so what I'm asking is that C is equal to 0. Let me go back. What does it mean that C is equal to 0? It means that E12 is precisely a multiple of E2, which somehow means that SU3, the copy of SU3, is an hypercompact subalgebra. Okay, let me explain this. It's a bit technical, but we can do it. So if you remember, I adapted the decomposition using the HJs and FJs, where HFJs was putting together the U1 coming from the abelian part and SU2. delta 1 is this. But what's more importantly is H2. Because H2 is going to be D2, delta 2, and F2. Right? Keep in mind this. Now, I have here, right? So if we have D2, delta 2, and F2, delta 2, E2, multiple, and F2, this is S3, right? So what I'm saying here is that I'm asking that S3 is not only a subadjoint, but it is an hypercompass one. Because the hypercompass factor put this together, giving the coping of H, and the action of this is controlled by all the T2s. So this is an hypercompass subadjoint. And it turns out that this is preserved by the body connection. So also in this case, I have a reduction of the holonomy because I have a copy, or I have a subspace, a subbundle, which is implicit a copy of S3, which is preserved. So also for S5, and this argument you can do for any S2 plus 1, you always have infinite many joint hypercompass factors with reduced holonomy. These three do not apply in dimensionality, right? Because, S3 cannot be non-trivial inside itself, let's say. But for S5, S7, and so on, I can do this. But, this is the most interesting thing. We also have something which is full. No, sorry, it was this. Okay. So for instance, if I pick the xanthoposis equation, so C now is different from 0, and I pick the easiest one, and so we have 1, 0, 1, 1, 0, then the holonomy is the full holonomy. Now, disclaimer, spoiler, not an elegant proof of this. We tried a bit, it was very complicated also because the dimension of this guy is 24. So doing it by hand, out of reach. We understood that this has to be the case with full holonomy. We weren't able to prove it. So at some point we got clever and we asked Maple basically. So we did this computation with Maple, but at least we understood that this has to be there to compensate with full holonomy. So why this case was, we were able to generalize this for any S2 plus 1. This is an isolated case. We know this for this hypercompass factor in S5. But we really believe that whenever C is different from 0, which is the exact opposite case, the holonomy is going to be full. And, okay, let me say one more thing, which I forgot. No, I think that I said pretty much everything. No, maybe you can see this thing. So, this is the first example in literature when you have an hypercompass manifold with left invariant hypercompass factor for which the holonomy has somehow a jump. Because here my holonomy is full, but here it is not. On S3 this does not happen because any left invariant hypercompass factor has full holonomy. Here it does. I have hypercompass factors with holonomy which is full, hypercompass factor with holonomy which is reduced. And actually this also proves that the reducibility of the body connection is not stable under deformation because they can move from one to another with a curve of hypercompass factors. Now I think that I said everything. And thank you very much. And also today is the Woman in Math Day, so okay.
It happened that in your classification, which might be very useful, all of them were the ones who practice the torus. It can't be a coincidence, I guess, that
this one is the bigger problem.
Is there, surely you can prove this directly, like, is there some invariant, could you actually write down the invariant subbundle of the tangent bundle?
You can write it down because, as okay, where is it? Since you obtain this by induction, you know precisely which fj is trivial. So you know this precisely. And if you want a concrete example, which is the example we started with, again, this was a funny story because it was me and Luda working and Giovanni was at home relaxing basically. And we were doing this example on SP2 times C2. And I messaged him and said, the holonomy is not full. And he replied, ha 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 ha, okay. We'll see tomorrow. It was not believing in me enough. So in this case, for instance, you have, the Delaunay algebra of the Bata connection. You can write this explicitly. And this is something of the kind, this is spontaneous dimension 3. So it's something of the kind that 0, 0, 0, 0, 0, 0, P1, P2, Q, where P1 and P2 is an imaginary quaternion, and Q is a quaternion. So it has some weird dimension. This has dimension 11, which is kind of weird. But this is the only example we got explicitly the Delaunay algebra. In all the because this has dimension 12, so it's painful, but you can still do computation. In Aga dimension, this guy had dimension that explodes. We know which subbundles are preserved because we can keep track of the trivial FJ samples. And also this tells us how much the Delaunay reduce, because you can count that. But the explicit computation of Delaunay only for this case, I'm sorry.
Yeah, no, it was more to do with whether there was one forms preserved or this. What those things were.
Thank you.
I'm not sure if the question makes sense, but is a full monomy the generic situation? Like if we deform a hypercomplex structure to nearby hypercomplex structures, do you expect?
Yeah, precisely. For instance, no. For this case here, this was the center of the deformation, and you move from here to something which reduces the Delaunay. If this was your question.
I mean, like in the case of Riemannian monomy, the generic situation is full monomy.
Yeah, I think here it's kind of the same.
To compute the monomy, is it? I mean, have you thought about using this approach of invariant connections?
Yeah.
In this place?
For doing this, we use left and right on the seeker.
Okay, great. So is it so you can explicitly write down what the Nomitsu map is for this connection?
Sorry, again?
You write down what the Nomitsu map is for this.
We didn't try actually, so this is a good idea.
And you can,
We did, for this we did root of force.
That's this formula which gives you the higher terms, and you add them all up somehow.
This is a good idea.
It's feasible. That might be.
Actually, for this we did a Bruce finger. So just computing the curvature, derivatives of the curvature, and so on. But probably with the Nomitsu map is going to be interesting. Thank you.
Yeah, I wanted to comment about the SLNH.
Yeah.
But you don't have full down on SLNH.
No.
That paper with Isabella.
No, repeat the one?
Yeah.
I'm sorry, guys.
It's some group of SLNH.
But it's inside
SLNH. The full SLNH is never realized.
No, well, here we say it's contained.
It's contained, yeah, but it's an interesting open question whether we can
full autonomy
realize SLNH in any hypercomplex manner. Because for me, manifolds, probably it should be always solvable. I don't know. I have a conjecture that for me, manifolds, it's solvable.
I never know. No, this is an interesting question.
There are lots of open questions.
So there was another construction of hypercomplex structure by choice.
Yes.
If I remember correctly, because this was long ago. You start, for example, from a quadratic manifold, and then you consider, so you don't have this IJK because it's they do not exist, but you have this rank 4 Salamo quantity.
Locally conforming.
Yeah, but so you can take the quotient of this bundle by some discrete subgroup and get something compact, and then Joyce can also take some twists of this thing, and on these twists he constructs this complex structures. So you may make this manifold simply connect, for example, by twisting. And then do you know anything about the holography of that?
Okay, we discussed this point because when we said what we needed for things and someone who suggested precisely this thing.
So is there in particular, I'm wondering, so I had an idea that there must be a connection between the only of the retreat on the planes on this quadratic.
I really think so. But I don't have a, let's say, exhaustive answer. It's a thing that when we got the reply, we said, okay, we should work, and we should work with this, but then we didn't really start. but it's a question that we want to address sooner or later. Thank you.
All right, so let's thank it again. Can we continue?
But we can make a noise.
All right, so let's start the last talk of the day by Mr. Pitt from IMPA. He's going to tell us about the percussions and quite diagonals in a product of elliptic curves. Mr.
Thank you very much. It's always a great pleasure to be in Campinas. I was there like almost 20 years ago for half a year, and we had great collaboration with Marcus and also with Sasha Nain, who was there. And it's also a huge pleasure always to be there because there's a nice interplay between algebraic and differential geometry, and in this conference as well. So I was trying to choose a topic which has both connections with torsion and algebraic geometry. I hope I will succeed. Yeah, so it's a joint work with our student Leila Bakarova, who is now in in Paris, and Sasha Kuznetsova, who is a professor in Moscow, and it's almost done. The problem is that last 10 days, internet in Russia is pretty much off. Government decided to turn off, so we can't come back. And we have a paper, but we need to finalize it and put it online. Okay. So I'm starting with algebraic geometry. We have a bunch of elliptic curves. So it's a product of elliptic curve, and inside that we have a curve, S functions. And then we fix a line bundle. So A is an line bundle on E, which is elliptic curve. And S is quite diagonal. So we project S to pi from S to elliptic curve. We take projection to number I. We take P star of our ample line bundle to S pi. And we want that all these bundles are equilateral torsion. So what we want is the pi of A times Pj star of A minus 1 is torsion. It's a very simple notion which we didn't find it anywhere in the literature, and asked people around. And I really would like that people who know classical algebraic geometry would look at it and tell me where it appears. Because in our case it appeared in very modern part, which is related to non-Taylor manifolds. So they correspond to project submanifolds, and soon I will tell about that. Non-Taylor homomorphic symplectic manifold. And in fact, what we proved that there are most countably many quasi-diagonals for any given elliptic curve and line bundle, and this was originally proved for non-tailored. The proof was used in non-tailored geometry. Now there is another proof which is classical algebraic geometry, but I still prefer the old one. Okay, so examples. I will explain that it's in the next slide that it's enough to produce quasi-diagonals in square elliptic curve. Then you can expand them into a product. There is sort of easy correspondence. But let's give an example. So example, you can do it with finite group, but suppose that you just have an order D automorphism. So nu from E to E automorphism. then we take its graph, and as a line bundle, we take L1 is any and line bundle, and we take A, which would be a product of mu power I star of A. Product of tensor for I. And this is clearly invariant under mu action. So it's an invariant bundle, and then if we take a graph of mu in P squared is that y diagonal. This is the reason why they are called y diagonals. So there's some explanation here, but it should be intuitively clear. So first observation is that we can take a fiber product of elliptic curves with quasi-diagonals. So if you have, first, if you have a quasi-diagonal in a product of elliptic curves, you project it to a product of two elliptic curves, it gives the image will be a quasi-diagonal. Which is very clear because full web computes with projections. And conversely, if you have a quasi-diagonal, it can be obtained from quasi-diagonals, like from this kind of product. You project your quasi-diagonal to a product of two, and then you obtain it from these projections by taking the product, and this is all quasi-diagonals. So quasi-diagonals are just obtained from curves in a product of two elliptic curves, which makes this problem super elementary. So it's strange that there are so many open questions related to quasi-diagonals. So quasi-diagonals can be obtained from products. Another notion which we will use a lot, I mean this is for everything is done for practical purposes, is restriction. Yeah, is the yes. And also there will be here there is a new count. So even the map x goes to minus x is quasi-diagonal, and the graph of our rotation is quasi-diagonal. Okay, so you have in power n the sigma map. I call it small sigma, but maybe it should be big sigma. It's just sum. So you take AI, A1 AN goes to sum of AI. Of course, for that you need to fix the zero in your elliptic curve, because it's not clear when we say elliptic curve, when we say elliptic curve with fixed, which is a group, or just genus one curve. So before I was agnostic and didn't fix it, now I fix it. Okay, so ZS is restricted. If S belongs to sigma minus 1 of 0. So for restricted we have some examples, but very few, because general pair EL has no restricted by the element. But there is one example. You just make a graph, x goes to minus s. This is clearly, well, you can check, it's not hard. It's by the element. For which line bundle? For line bundle A, which is O of unity, or power point. Another is you can take a graph of you have order 3 automorphism, you take its graph in E3. This kind of map. And again, we'll take a bundle of E that lifts to this E in the same way, and then it's also the sum of these 3 points is 0, so it's a can take fiber products. So if you take, for instance, this anti-diagonal several times in fiber product in En, for even n, this gives you right diagonal. For what you can take this one in E3 and then the one in E2 several times, and this will give you examples of restricted by diagonal. So for each any integer starting with 3, sorry, should be 3 here, we have a restricted by diagonal. Now questions. Questions? No loss. Yeah.
No, because you keep saying a product of elliptic curves. But actually consider the product of the same elliptic curve.
Yes.
Right?
Thanks. Of course. Thank you very much.
Because for this it's clear that it has to be the same elliptic curve. But before, in general, you can consider different elliptic curves.
Yeah, and then, but then you need to identify somehow the line bundles. Yeah, it makes sense actually to ask this question because everything is related to correspondence. So why don't? But in practice, we have all the same elliptic curve. So yes, thanks. Okay. So open questions. So the first is okay. We have a bunch of elliptic curves. So we have lots of different ones. And there are some examples which are elliptic and similar. But so far we didn't find any curves with geometric genus. Now, another is that I told you these examples of restricted diagonals, and they all related to a total bundle. Total bundle here means that it's a bundle which is commensurate of E. So the question is, can we have other line bundles? Still unknown. Another, okay, you have, I discussed, describe you the even, for even products of elliptic curves. We have this anti-diagonal, which gives you restricted, but for odd ones, we have only the curves of multiplication, so it's still open question. I think there are none, but can we have, and for, yeah, and also we have just in EC we have just one restricted by diagonal. So the question is, can we have anything else? It's a very funny question which probably should be tried by some beginner students of algebraic geometry. Probably they are not extremely hard, but we didn't spend too much time on it because we were focused on just existence and non-existence. And
so, can I ask some questions?
Yes.
So, I mean, let's say that if you have a complex multiplication, is it true that algebraic cycles are related to quasi-diagonal?
In the product? Good question. So, I think in practice, yes, but we didn't check. But we did, you said we did this very elementary question, so we couldn't answer it. Yeah, it's a classical notion which was missing from the literature and from research for some reason. Let me explain why we care. So there is something that Andrea already mentioned. So we have, if we have a complex surface, we can take its symmetric power and resolve the singularity. And a surface the and Hilbert scheme is a resolution of and quotient by symmetry. And what is important that, well, we should identify this Hilbert scheme with ideal shapes. This why it's called Hilbert scheme. And then it's sort of clear that if M is holomorphic asymptotic, then Hilbert scheme is holomorphic asymptotic. And they mentioned that as well. So the examples is K3. K3 is it's Hilbert scheme, it's simply connected homomorphic vector. So it's maximum how long the hyperpedal may. For a torus, we need to do something, which I mentioned. So if you take a Hilbert scheme, it's not true, it has a balance map, just a sum of points in that. So if you have a torus, it's mapped to T and quotient by symmetric group, and this maps to a torus just by summing up the coordinates. You take primitive point, and it gives you general sum. So these are two main examples of hyperpedal. And then there was a conjecture order, which is completely, even for small deformations of hyperpedal manifolds, is still open. And Todorov believed, and he just mixed up some numbers. And his so proof was nice, but can't recover there. That any complex interconnected homomorphic syntactic manifold is scattered, and pretty much at the same time as he published the preprint, one constructed counterexamples, which were not. So Bogomolov did counterexamples of one nicely using the construction similar to Hilbert schemes, but for codirections. And this gives the only known example of non-chaos interconnected homomorphic symplectic manifold. Okay, so codirected surface, let me give you a construction because I'm going to use it a bit, and it's also related to elliptic curves and line ample bundles on them. So suppose you have a ample bundle, or you can add them. The very important thing that C1 is not zero. On E, let's call it, here it will be Q1 mainly. Well, it's not Q1 yet, but it will be one there immediately. We take S without zero. It's C star 1. So it's C star fiber over E. So it's not zero vectors. And then we take a quotient of this, let's call it tot A to signify non-zero vectors, and we take its quotient by so by x goes to t goes to lambda v, where absolute value of lambda is bigger than 1. This now the fibers which were C star become C star quotient by z. So this is elliptic curves. So this is elliptic curves fiber over elliptic curve. This called Kader-Thurston or Kader.
So you take the simply connected.
No, it's not simply connected because it's fiber of elliptic curve. In fact, it's P1 is equal 3.
I meant, is there a torsion in the
The next slide. Right now it's P1 equal 3, so it's so P1 equal 3, it's non-header. And it's pretty much easy to see that it's non-header because you have your C1 of your ample line bundle. It becomes 0 on that because on this case without 0, the line bundle has a section.
Is that because B1 is 3?
So the line bundle becomes trivial on this total space of A without 0.
Reason B1 3?
B1 is 3. No, yeah, B1 is 3. But so your Keller formula becomes trivial on the Kadar surface. And then it's topologically trivial. Of course, it's a positive form. So if it were Keller, you would multiply it by your exact 114, and it will be, has to be positive, integral has to be positive, but it is zero. So this is kind of okay. And generally, if you have vibration, then pullback map is injectable homology. It's a theorem of, I suppose, the lead. So in that case, it's clearly not. And now, starting from Kadar surface, you can repeat this construction with Hilbert scheme and obtain this Gamma 1 manifold. So the idea is that first we take the slippers. For elements of a diagram, or code, we take code N, it's slippers. It's homomorphic synthetic. But it's not simply connected. We want something simply connected. So we consider we do construction which is similar to construction which was used to for the giant scalar, giant Kummer. So we projected to U. So suppose that the diagram was fiber with fiber E1 or E2 over E1. We projected to first we projected to E1 to symmetric power of E1. So it's E1 power n quotient by symmetrical. And then we projected by summing the points to E1. And we take image of 0. So D inside of n is image of 0. It's a divisor. And the divisor in a homomorphic symplectic manifold, it has a canonical foliation, which is a kernel of your homomorphic symplectic, of your symplectic form. In our case, it's homomorphic symplectic form. So it's called characterize foliation. It's the all 5 vectors which are orthogonal to D. So tangent space of to D orthogonal with respect to homomorphic symplectic form. It is contained in D. And it's the tangent space of D. It's one dimension. And we take a quotient by this foliation. So this foliation, it's not hard to see that it's, so you have E2 action on the fibers. E2 is the second curve, which, and this color surface is actually principal fibration with fiber E2 and base E1. So you take this quotient, so the leaves of that are fibers of E2, and you take D quotient by and this homomorphic symplectic. Because always, if you have device on the side, homomorphic symplectic, you take a quotient. The leaf space of the characteristic foliation is homomorphic symplectic. And what you obtain at the end, of course, this foliation is locally smooth, but globally it's not smooth. You would have some orbital singularities. But if you choose your numbers right, this orbital will have that covering, final covering, which is smooth, and it's called Gamow line. So it's complex, interconnected, homomorphic symplectic, and it's like a third branch of this 2 series of hyperkähler manifolds, which Andrei told us today. Interesting of case 3, and the third one is called Gamow line. It has very nice properties, so it has the same deformation theory as hyperkählers. It also has this Gamow by big form and many other nice things about it. So today I was interested in classification of algebraic varieties of Gamow lines. Of course, it's difficult because it's quite terribly complicated because of similarities.
Yes.
So, yeah.
Is there an interpretation of this information of some modular spaces of some homomorphic symplectic Kähler manifolds?
Gamow 1 from homomorphic symplectic Kähler?
Deformations.
There was an idea, but it's not proven, that if you take the generalized Kummer fiber over CPN and you do the straight state twist, you obtain this gas. Probably it won't happen because of this fine covering. You need to resolve it. Literally, it's probably false.
So it cannot be, in a way, considered as an analogy of O'Grady construction.
Well, it's a series, and for O'Grady, so far it's not obtained by any as a modular space of time.
That's what I was asking.
Don't think that B3 ports or something like that.
B3 is one. Oh, B3 is one. But B3 is not for Discrete.
So I mean, they are not deformations, but it's V.
Okay. And B1 is
One is zero.
B1 is 0, but H1 0 is non-zero, so it's already non-deformation. Yeah, so you can compute the Hodge numbers. It's very easy and very nice computation. Okay, so I care about precursor. Why? So it's so simple. We don't like it. We want to have a, and since we are interested in homomorphic subvarieties, we will consider a manifold which is nice, smooth, and you don't need to resolve anything, and it's equivalent to our manifold by doing some blow-ups, blow-downs, and essentially resolving singularities and taking some final unified dynamics. So we take just for that power n. It's projected to into power n, and we take into power n. We take it's projected to so you have the fiber is E1 power n, and we take the image of the zero. So you have a P inside what power n with three images. And we take big motion by E1. It's Gamal 1. It's homomorphic asymptotic, and instead of classifying subvarieties in Gamal 1, we will classify subvarieties in that, and this is there's an equivalence. So it's of course it's no longer simply connected. In fact, it's a new manifold, but it still works very nicely. Okay. So the theory now. Yeah, you can also have non-restricted Gamal 1 precursor, which is just a quotient of code and quotient by E2. It's non-restricted. Yeah, by the way, I think I mentioned it somewhere, but there is another important paper which was preceding our paper with Kuznetsov and Bakarova, which is a paper of Bogomolov, Kuznetsov, Albornosov, and Yasinski, who did it for Keller. So they classified Keller and Fuji class C submanifolds, and we classified projective. Okay, so this is non-restricted precursor, this is restricted precursor, and theorem. If you have Z inside precursor, Z is projective, or moisture zone, doesn't matter. If and only if its image in E2 power n is equatorial. So for restricted precursors, which are really correspond to Gamal 1, it gives restricted polynomials, otherwise it is not restricted. And the proof is actually very easy. So you have this fibration is just a product of elliptic fibrations obtained by taking line bundle and C-star bundle and taken quotient by Z. If such vibration has sections, just because it's principal vibration, if it has multi-section, then it has a power which is triple. And if you look carefully, this gives you precisely this equivalence between two bags of lamps. Because of course, if it's projective, it gives you a multi-section, and conversely, if it has multi-section, it's projective. Okay, so this is how we study this. The point is that they are Neiman. So what is a Neiman? It's a beautiful and great example example of the whole differential geometry which were well already seen these 2 days, but nobody mentioned them much, so I had to introduce them. So we start with the nilpotent Lie group, and we take its quotient by which is co-complex. But on the other hand, we can just define the manifolds as any manifold which is homogeneous under the nilpotent group. It's the same by mass. Also, you can produce them from Lie algebra. So you have a Lie algebra, inside that you have a Lie sublattice. And then you take exponent of this sublattice because we are in a manifold, the group is nilpotent, so exponent is just polynomial, and you can take the quotient of your, and this gives you the manifold as well. So it's just, essentially the category is equivalent to category of rational important equals.
So did Mauser formulate this statement like that?
Sorry?
Did Mauser formulate this statement like that?
Actually, he was very modern. Not like that, but very close.
I think the manifolds probably as such appeared later.
Probably, yeah, but he was very, very surprisingly close to the modern understanding. So the other thing is that there are only iterated cycle patterns. So the circle patterns, so the topology is very simple. I won't have time to explain this topology in big detail because there's no time. But let me spend a couple of minutes at complex structures. So there's something that Beatrice already introduced, that if you have any group, you can have left invariant complex structure, and it corresponds to some subalgebras in the corresponding Lie algebra. Because what is a complex structure? It's just a sub-bundle with a divide tangent bundle. So, but since it's step invariant, it's also subspace in computation of the Lie algebra, and you have your Lie algebra decomposed into Lie G10 just positive partition plus the complex simplified Lie algebra G01, and the integrability is just this large subalgebra. So this gives you a very nice understanding of what is left invariant complex structure, and then you can take a quotient. You have left invariant complex structure, take a quotient by left action of the discrete group, this gives you min-min. It's an extremely beautiful example of complex, which is never kept, and never Münch, never nothing. So Godard example is Godard surface is an example. I won't have time to deal with that, but there's a beautiful formulas which explain why. And there is also a nice paper of Kasigawa which just specifies all surfaces which are universal manifolds or nil manifolds. Yeah, it's an introduction, and it's a survey, but it has all formulas done in a nice style which is written. So the idea is that Godard topologically is just Heisenberg manifold, Heisenberg group quotient by discrete group, so it's like 1, 1, 1, A, B, C, this kind of group, quotient by discrete subgroup, and then multiplied by zero. And then you can, using that, you can write this toric over toric foliation, fibration very explicitly in terms of the algebra as well. So it's another construction of Godard, which is it. Okay, the point is that this construction, if you apply that to our precursors, gives you precursors are also obtained as denied, both restricted and non-restricted. So I want to apply this. For that, I will tell you a couple of words about Barley spaces. I have pretty much no time, so the idea of Barley spaces, we'll care only about curves, but it makes sense for anything. So Barley space is just a space of subvariables. Since we're in a complex situation, it's difficult to speak about them as moduli Rodrigues style, but still there are two ways of producing complex structure on space of cycles. Barley and duality is subschemes, and Barley is just cycles. It's like hybrid scheme and symmetric power, hybrid jaw constructions. Good thing about Barley is that we know it's complex. Well, we know everything about it because there's a huge book by Barley and Anderson explaining all details. And there's important thing that there's closure topology, just the distance between your cycles. Like one cycle is an epsilon neighborhood of another is an epsilon neighborhood of the first. Gives you your topology which is compatible with complex structure on this Barley space. There's a theorem of vision which says that if you have a Barley space of T cycles with bounded volume, it's compact. So the limit of cycles with bounded volume in Barley sense is again cycle in the same Barley space. Why it is in this? You will see. But for the moment, it is important because on the Bogomolov 1 we can produce a metric which makes the model complex curve compact. The Barley space of complex curve compact. So SKT, this is actually the torsion metric, which were already mentioned today quite a lot. So omega is SKT if dc omega is 0, or the torsion. Well, you have a canonical torsion connection, and this torsion should be closed. So it's Bohl's talk. Okay. And then they have this particular metric can be applied very nicely. So Bishop Gromov, which was actually previous slide was called Bishop, but Gromov did it for almost complex. If you have the space of all complex curves with bounded volume, then it's compact. And then if you have a complex manifold equipped with very closed form and X is component of the model of complex curve, Barley model, then it's also compact. So if M omega is SKT, Barley space of curves is compact. Okay, the reason is that if you even easily check that the function, the volume function on the Barley space would be purely harmonic. It will be satisfied DDC of so DDC of all DDC of the bar of all is 0. It's what is called pure harmonic function, and pure harmonic function can have maximum or minimum. If it has maximum or minimum, it's constant. Non-zero. So it has to be constant. One by hope, strong maximum principle. On the one hand. And then this implies that the volume is constant on every kind of component of Barley space, and then it's compact Bogomolov. Now I will explain that the Bogomolov 1 precursor is SKT. That's a computation. Let's forget the computation. Just think about the surface. So surfaces, for complex surfaces, the DDC of omega is constant, is volume. DDC of omega is volume. But now we are on Kodaira. Kodaira is homogeneous, globally homogeneous, so DDC of omega should be either positive or negative or 0. It can be positive or negative because it's exact. So it has to be 0. Such metrics are called conditional. And this, they are always SKT. Now, our Bogomolov precursor are products of So the idea is that you prove that DPC, you compute DPC of omega square, and then you push forward of omega square downstairs under your two action, and this gives you a schematic on gamma 1 vectors. Okay, this gives us something. Namely, we know that the multi-space of curves is compact. And there was a very nice work of Capana, who, so he was like one of the originators of the notion of rational connectedness. Rational connected manifolds are manifolds where you can put rational curve through every two points. But when he did that, he did actually a way more. So he was exploring what happens if we can connect points in the manifolds with rational curves at different time. So this includes this moisture zone. So moisture zone manifold is a manifold which is biparamorphic to variational to rigid. And what he proved, what Manan proved, is that if you have M is projected to B and fibers are moisture zone, and B is moisture zone, then M is moisture. Which is highly non-trivial, and I explained that by referring to his other works, but the statement is simple. So I would go to the next slide and apply that to our precursors. So I'm proving that there are finally many bidiagonals. No, can't be many bidiagonals.
I don't see a little bit what the meaning of the word torsion is.
Torsion? It comes from the following reason. So if you have, you're missing probably the axis in the middle of the data. So if you have an emission complex, there exists a unique connection of number, such called Bishop connection, such that number of omega is equal to 0 and number of I is equal to 0. And it has its torsion of omega satisfies. So you take, apply the torsion to x, y, and you take this gives you a vector, and you take this vector product, and it should be antisymmetric. So this is a 3-form, which is called torsion 3-form. Let's call this, and then this torsion 3-form is dc of omega. With some constant, maybe minus or
Minus signs.
but not two, just minus. And if it's closed, it's called SKT because the place is onto role in the standard equations. So now you can write billions of papers and make hundreds of billions of citations from this, which many of our friends do. But it's still, regardless of applications to physics, it's a good notion from us. As you would just see, because I used that without any physics to prove a theorem. So let me prove the theorem in the last 3 minutes which I have. So the theorem says that there are currently many bidiagonals. Many bidiagonals. Okay, so cool. We have our gamma quantum precursor fiber with a fiber P1 over times C2. And we know that the pre-image of if you have a quasi-diagonal S in there, this pre-image is projected. Suppose that S live in a family. So they are not countable in any but uncountable. This means that you have a family covering this C2 times C2. So you have ST, which covers C2 times C2. But then the pre-image of each ST is actually a product. It's a principal bundle. And the principal bundle E1 times. So if it has a section or multi-section, it has the whole set of multi-sections. And this means that you have every points are connected by a bunch of curves, and which form, in fact, you have a vibration which has motion on fibers and motion on plates. The co-reduction of component gives you that this diagonal bond reversal is motional, as long as you have this sufficiently many quadrilaterals. And this is possible because minimalities can be motional. This is an application of torsion geometries called Rodrigues. And I'm done. Thank you very much.
More questions?
I have a curiosity in a sense. Do you know if Bogomolov-1 miracles are formal, or if they're, if the Bogomolov-1 precursor is formal?
I think it's formal for lower terms and it's not formal for higher terms.
Okay.
What we proved is that there's a DDC theorem for third number,
Okay.
which is enough to do deformation theory. So this is how we proved. But I think for higher it's way more complicated because Fodara is non-formal, it has non-trivial massive products, and I think you can carry over the massive products for Gamma 1.
Okay.
Do you know if there are finite remaining?
This is a question. We did, for non-restricted, you can actually produce quantum many. We did it. I didn't write about that, but it's in the paper. But for non-restricted, we don't even, no. For restricted, the examples are very scarce. So in general, just have no.
So did you say something like that this course is algebraic if we don't use around quadrilaterals or?
So pre-image of quasi-diagonal is algebraic, and conversely, if something is algebraic, then its image is quasi-diagonal.
And so then what's the relation between this and the subvarieties in the Bogomolov-1?
It's the same in Bogomolov-1, except for Bogomolov-1 instead of productivity curve, you have productivity curve by symmetric, which is CPN. So you have curve in the CPN, you put it there, and then we have better. So if you have, so Bogomolov-1 is a Lagrangian fiber over CPN. If you have algebraic separated Bogomolov-1, it gives you its image as a curve, which corresponds to a quasi-diagonal in the fiber. Thanks for asking, I forgot to tell. It's important. It's actually quite funny because Bogomolov-1, all fibers are projective. The base is projective, but they somehow glue together in such a way that there are no algebraic separatives and curve. And then also the scalar, also if the subvariety which is G plus C or Taylor, the image is also. So there are almost no Taylor separatives at all, or G plus C.
Okay, if there are no more questions, let's take
Thank
the
you.
session.
Tomorrow
start at 9 back in the main building, and now